Look up at the night sky on a clear evening, and you'll see a familiar tapestry of stars, pinpricks of light against a silent, dark canvas. It's a view that has inspired humanity for millennia, filled with myths, dreams, and the quiet reassurance of cosmic order. But what if I told you that beyond this familiar dome lies something stranger, something older, something that defies everything we think we know about the universe? Scattered across the unimaginable distances between galaxies are structures so immense, so precisely arranged, and so bafflingly complex that they challenge not only our science, but our very understanding of reality itself. These are not just random clusters of stars or clouds of gas. These are formations that seem engineered, organized, almost intentional. We're talking about cosmic mysteries on a scale that's almost impossible to visualize. Picture filaments of galaxies stretching billions of light years, threading through the cosmos like the veins of some celestial giant. Envision strange, repeating radio signals echoing from the void with mathematical precision, or vast bubbles of energy with no clear source. These aren't science fiction, they are real, observed phenomena that have left even the most brilliant astronomers scratching their heads, wondering if we're missing a fundamental piece of the cosmic puzzle. What force could weave galaxies into patterns spanning nearly the entire observable universe? What intelligence, if any, might be behind signals that repeat like a cosmic heartbeat? This video is an invitation to journey beyond the edges of known science, to explore the most mysterious structures in intergalactic space and the profound question of who or what built them. We'll venture into theories that range from the awe-inspiring to the mind-bending natural cosmic phenomena operating on scales we barely comprehend, or perhaps evidence of something else entirely. Something that pushes the boundaries of imagination. This isn't just about astronomy. It's about rethinking our place in the cosmos and daring to ask if we are truly alone in a universe that seems, at times, almost too well arranged to be accidental. So settle in, open your mind, and let's begin this exploration into the deepest enigmas of space, where every answer only leads to more breathtaking questions. To truly grasp the enormity of these intergalactic puzzles, we first need to understand the stage on which they appear. The space between galaxies isn't just empty, it's a profound, almost unimaginable void. While our own Milky Way galaxy is a bustling metropolis of hundreds of billions of stars, the gaps between these cosmic cities are deserts of near-nothingness, spanning distances so vast that light itself takes millions of years to cross them. It is within these immense, dark oceans that we find the strangest islands, structures, and signals that simply shouldn't be there according to our conventional understanding of physics. What sets these phenomena apart is not just their location, but their sheer, unnatural scale and their seemingly organized, almost architectural nature. A swirling nebula within a galaxy is a wonder of natural forces, gravity and radiation sculpting gas and dust, but a perfect, gargantuan ring of galaxies, or a synchronized flash of energy repeating from a billion light-years away, these are different. They feel less like natural formations and more like something designed, or at the very least, orchestrated by laws of physics we have yet to discover. Our ability to even see these anomalies is a testament to human ingenuity. For most of history, the deep voids between galaxies were just that, voids, invisible to our eyes and early instruments. The revolution came with space-based telescopes like Hubble, and more recently, the James Webb Space Telescope, which act as time machines, peering not only across incredible distances, but also billions of years into the past. Satellite observatories tuned to see X-rays, gamma rays, and radio waves have peeled back another layer of the cosmos, revealing an invisible skeleton of energy and matter. We can now map the large-scale structure of the universe, and that's where the true mystery begins. Instead of finding a random, splattered distribution of galaxies, we see a cosmic web long, thin filaments of dark matter and galaxies stretching across the universe, connected at nodes like some immense neural network. The scale is baffling. These structures can be hundreds of millions of light-years long, a size that defies the natural pull of gravity acting alone since the Big Bang. It's as if we've discovered the blueprints for the universe, but we have no idea who the architect is or what tools they used. This isn't just an academic curiosity. These mysteries are the sharp edge of science, prying open new fields of study and forcing us to question everything. They are the anomalies that, throughout history, have always preceded a paradigm shift in our understanding. The precise nature of these formations might be our best clue to unlocking the secrets of dark matter, the invisible glue holding galaxies together, or dark energy, the mysterious force ripping the universe apart. Or, in perhaps the most profound possibility, they could be evidence of something else entirely, not just unknown natural forces, but the fingerprints of an intelligence operating on a scale we can barely comprehend. The idea isn't that some alien species built a ring of galaxies, but that a sufficiently advanced civilization might manipulate matter and energy on a cosmic scale, leaving signatures in the very fabric of space-time that we are only now learning to read. It's the difference between finding a strange, eroded mountain and finding a pyramid. One is a wonder of geology, the other is a testament to intention. Think of it like this: if you were an ant on a vast, sandy beach, the dunes and ripples would be your entire world, shaped by wind and water. But if you suddenly saw, etched across miles of shore, a perfect geometric pattern or a message written in stones, you would know instantly that it wasn't created by the same forces that made the ripples. You would recognize the signature of a guiding hand, an intelligence from entirely outside your understanding of the beach. In many ways, that is the position humanity finds itself in today. We are the ants, and we are just beginning to look up from our local ripples of stars to see the impossible patterns written across the cosmic shore. These intergalactic mysteries are the stones, and they hint that the universe may be far stranger and far more purposeful than we ever dared to dream. Our journey into the unknown begins not in the far reaches of the cosmos, but much closer to home, with a force that is actively pulling us and everything we know toward an unseen destiny. Imagine for a moment that you're floating on a vast, calm ocean. The water is still, the horizon is clear, and yet you feel an undeniable current tugging you relentlessly in one specific direction. No matter how you paddle, this invisible river carries you along. This is precisely the situation our entire galaxy finds itself in, caught in the gravitational current of a cosmic mystery we call the Great Attractor. The story of its discovery begins not with a flashy image, but with the careful, meticulous work of mapping the universe through redshift surveys in the 1970s. Astronomers were measuring how the light from distant galaxies was stretched or redshifted as they moved away from us due to the expansion of the universe. This created a map of cosmic motion, and it was on this map that they found something deeply unsettling. Our local group of galaxies, including the Milky Way and Andromeda, along with thousands of others, were not moving apart in a perfectly uniform way. Instead, we were all being pulled sideways toward a specific point in the sky near the constellation Norma, as if by some immense, unseen hand. The sheer force required to move entire galaxies against the backdrop of the universe's expansion pointed to a concentration of mass so colossal it was almost incomprehensible, a gravitational anomaly of epic proportions. Yet the most frustrating part of this mystery is its location. This immense pull is centered in a region of the sky astronomers poetically call the zone of avoidance. It's not a forbidden zone or a cosmic barrier, it's simply the plane of our own Milky Way galaxy. From our perspective, it's like trying to see a distant mountain range through a thick, perpetual fog bank. The dust, gas, and dense field of stars in our own galactic disk completely obscure our view of what lies beyond, effectively blinding our optical telescopes to the very heart of the anomaly. It's a cosmic irony of the highest order. The answer to what is pulling us is hidden behind our own home. So what could it be? The leading theory, championed by pioneering astronomers like Alan Dressler, who led the groundbreaking Seven Samurai study, is that the Great Attractor is a supercluster of galaxies, a massive knot in the cosmic web where the filaments of dark matter and galaxies converge into an overwhelmingly dense node. We now know it's part of an even larger structure called the Laniakea supercluster, of which we are merely an outlying suburb. But even this immense collection of normal matter might not be enough to account for the incredible gravitational pull we feel. This has led to other, more exotic ideas. Could it be a concentration of dark matter so vast it defies our models? Or, more radically, is it evidence of a flaw in our understanding of gravity itself? A crack in the foundation of Einstein's theory of general relativity on the largest scales? The implications of this unseen force are profound, forcing us to confront fundamental questions about the fate of our cosmic neighborhood. Are we and thousands of other galaxies simply being drawn toward the universe's largest dinner party, a natural gathering of matter? Or does the precise, overwhelming nature of this pull suggest something more, a deliberate funneling, a cosmic mechanism whose purpose we cannot yet fathom? The Great Attractor is a humbling reminder that we are not still, not isolated, but passengers on a galactic ship sailing on a current we cannot see toward a destination we cannot yet know. It is the perfect entry point into the unknown because it proves that the greatest mysteries aren't always billions of light years away. Sometimes they are pulling us right now, hidden in plain sight, or rather, hidden just out of sight behind the brilliant veil of our own Milky Way. But if the Great Attractor shows us an unseen force acting upon our local neighborhood, then the next structure on our journey shatters our perception of the universe's very architecture, revealing a formation so immense it seems to defy the fundamental rules of cosmology itself. We are venturing beyond any local pull into the realm of the truly colossal, to a structure known as the Hercules Corona Borealis Great Wall. The name itself evokes something from myth, and the reality is no less staggering. This is not a wall of stone or ice, but a vast filamentary conglomeration of galaxies, a sprawling cosmic continent stretching over an almost unimaginable 10 billion light-years from end to end. To put that incomprehensible scale into perspective, if our entire observable universe is a sphere roughly 93 billion light-years across, this single structure occupies more than a tenth of that entire diameter. It is, by any measure, one of the largest single entities humanity has ever identified, a leviathan woven from the fabric of space and time. Its discovery is a story of modern cosmic detective work, and it didn't come from looking at starlight, but from mapping the most violent and energetic explosions in the cosmos, gamma-ray bursts. These are the death cries of massive stars or the collisions of ultra-dense neutron stars, events so brilliant they can outshine an entire galaxy for a few fleeting moments. A team of astronomers, including Istvan Horvath, were meticulously charting the locations of these bursts, expecting them to be randomly sprinkled across the sky, a final, fiery punctuation to the lives of stars distributed evenly throughout the universe. Instead, they found a shocking pattern in the northern sky within the constellations of Hercules and Corona Borealis. The map lit up with an astonishing and dense cluster of these events. It was as if they had found a specific neighborhood in a vast, dark city where cosmic violence was happening on an unprecedented scale, pointing to an underlying massive structure absolutely teeming with galaxies. Horvath himself noted the profound implications, stating that the feature was too large to exist. It challenges our current understanding of the universe's evolution. And that is the true heart of this mystery. This Great Wall doesn't just break records for size, it seemingly breaks a cornerstone principle of modern cosmology, the cosmological principle. This is the foundational idea that, on a sufficiently large scale, the universe is homogeneous and isotropic. It should look roughly the same in every direction and from every location. There should be no preferred center, no grand structures, no special places. Matter should be evenly distributed once you zoom out far enough. The Hercules Corona Borealis Great Wall is a screaming contradiction to this principle. A structure of its size and mass simply should not exist. It is a cosmic irregularity on a scale that our best models of the Big Bang and the subsequent evolution of the universe cannot comfortably explain. It is an anomaly that forces a profound and uncomfortable question. Is our universe truly uniform, or is it lumpy, textured with features we are only beginning to perceive? So what could possibly create such a monumental flaw in the cosmic tapestry? Scientists are grappling with several theories, each more fascinating than the last. The leading idea points back to the universe's very first moments, to a period of rapid inflation. During this immeasurably brief time, quantum fluctuations, tiny, random variations in energy, were stretched to astronomical sizes, potentially seeding the universe with the initial irregularities that would later grow into such vast structures under the influence of gravity. The Great Wall could be a fossil, a preserved imprint of the universe's quantum origins, a fluctuation that won the cosmic lottery and grew to an impossible scale. Others propose even more exotic explanations, such as primordial defects in the fabric of spacetime itself, cosmic strings or textures left over from the early universe's phase transitions, around which matter preferentially coalesced. And then, of course, there is the most speculative yet utterly captivating possibility that such a structure, by its sheer scale and apparent organization, could hint at something beyond natural processes. While no serious scientist is claiming it was built by hands, some thinkers in the realm of advanced theoretical physics ponder if a civilization of a truly unimaginable technological maturity could, over billions of years, influence the distribution of matter on a galactic or even supergalactic scale. Could such a structure be a signature of cosmic engineering, a project so vast its purpose is beyond our comprehension? It is a thought that pushes the boundaries of science into the realm of philosophy, forcing us to consider not just how the universe works, but if there might be other wills at work within it. The Hercules Corona Borealis Great Wall is more than a list-topping astronomical fact. It is a profound challenge. It asks us to reconsider our most basic assumptions about the cosmos, suggesting that our maps are still incomplete and our theories are still evolving. It is a humbling reminder that the universe, in its infancy, may have operated by rules we have yet to fully decipher, leaving behind relics of a time and a scale we are only just learning to see. It stands as a monument to the unknown, a cosmic sphinx whose riddle we are only beginning to understand, and its silent presence in the depths of space compels us to look even deeper for answers. If the Hercules Corona Borealis Great Wall represents a challenge to our understanding of the universe's large-scale structure, then the next mystery we encounter is one of pure, unadulterated form. It asks a different kind of question, not about the size of things, but about their shape. What if the cosmos, in its silent, infinite expanse, began to draw perfect circles? This is not a philosophical thought experiment. It is the reality of a discovery that has left radio astronomers both thrilled and utterly perplexed. They are known as odd radio circles, or ORC, and they are perhaps the most visually striking and enigmatic phenomena to emerge in modern astronomy. Their story begins not with a slow, building curiosity, but with a moment of sudden, brilliant confusion. In 2019, astronomers using the Australian Square Kilometre Array Pathfinder, or ASCAP, telescope were conducting a vast survey of the sky at radio wavelengths. This telescope doesn't see visible light. It sees the universe in the long, low-energy waves emitted by some of its most energetic processes. While sifting through their data, a team led by astronomer Ray Norris encountered something they had never seen before: faint, ghostly, and absolutely massive rings of radio emission. These were not smudges or blobs, but distinct circular structures like ripples frozen in a cosmic pond. The initial reaction was one of pure astonishment, followed by a process of elimination that only deepened the mystery. They were not the remains of supernova explosions, which are often spherical but are filled with chaotic, visible structure. They were not planetary nebulae, the beautiful dying breaths of stars which are far too small. They were not Einstein rings, those gravitational mirages caused by warped spacetime. Each known category was checked and decisively ruled out. These were something entirely new, and they had simply appeared on our maps of the sky without any explanation. The scale of a single ORC is enough to inspire awe. These are not small features. They can span hundreds of thousands of light years across, meaning a single one could easily engulf our entire Milky Way and its neighboring galaxies within its circumference. Perhaps the most haunting detail is what lies at their heart. Many of these perfect radio rings are centered on a distant galaxy, often one that is otherwise unremarkable, quietly humming along without any visible cataclysm that could possibly be responsible for creating such an immense, energetic halo. It presents a surreal image, a seemingly normal island universe encircled by a silent, invisible Titan's ring, a structure so vast it defies the very event that might have created it. This eerie perfection is what makes them so compelling. They feel like artifacts, like cosmic signposts pointing toward a physics we have not yet learned. So what process in nature could possibly sculpt such enormous, precise, and temporary-seeming formations? The hunt for an answer has spawned a spectrum of hypotheses, each more fascinating than the last. The leading natural explanation involves shockwaves. Imagine a truly colossal event at the galaxy's core, such as the simultaneous eruption of millions of supernovae, or a starburst period of such ferocity that it sends a spherical wave of energetic particles screaming outward at nearly the speed of light. This wave would expand for eons, cooling and fading until all we can detect is its faint, circular leading edge, the ORC we see today. Another theory points to the cataclysmic merger of two supermassive black holes, an event so energetic it could send gravitational ripples through space-time that themselves energize intergalactic gas, causing it to glow in radio waves as a perfect, expanding sphere. But the theories don't stop with known astrophysics. Some researchers have ventured into more speculative territory, pondering if these could be the throats of wormholes, those hypothetical shortcuts through space-time, though what physical mechanism would make them appear as faint rings is anyone's guess. And then, of course, there is the most profound and challenging possibility: technosignatures. Could ORCs be the result of activity by a Type 3 civilization on the Kardashev scale, a culture that has harnessed the energy of its entire galaxy? Perhaps these rings are the aftermath of unimaginable engines, the signature of galactic-scale transportation networks, or even the residue of a contained energy source we can't begin to comprehend. While this remains a highly speculative last resort for explanation, the very fact that it can be seriously contemplated highlights how thoroughly ORCs have disrupted our categories. They are a blank space on our map of the cosmos, and in that blank space, every possibility, from the ultra-violent to the ultra-advanced, must be considered. Odd radio circles are more than just new objects. They are a new language. They are a form of cosmic communication, not from aliens, but from the universe itself, telling us that there are entire chapters of astrophysical events, violent, beautiful, and transient, that we have not yet read. They challenge our need to categorize and immediately understand, reminding us that discovery is not just about finding answers, but about finding better, more profound questions. They are the ghosts in the radio machine, perfect circles drawn on the void, and they invite us to look deeper, to listen more carefully, and to wonder what other impossible shapes the darkness might contain. While the Hercules corona, Borealis Great Wall, and the odd radio circles exist in the profound depths of intergalactic space, our next discovery brings the mystery shockingly close to home, emanating from the very heart of our own galactic city. Imagine looking up at the night sky and seeing not just stars, but two colossal, symmetrical lobes of invisible energy, towering 25,000 light-years above and below the serene disk of the Milky Way. You wouldn't see them with your eyes, but if you could perceive the high-energy gamma rays that illuminate them, you would witness an hourglass of pure power, a silent monument to a cataclysm of unimaginable force that erupted from our galaxy's core. These are the Fermi Bubbles, and their discovery revealed that our seemingly tranquil galaxy has a violent, explosive past that we are only just beginning to understand. The story of their discovery is a masterpiece of modern data analysis, a testament to finding the extraordinary hidden within the ordinary. The Fermi Gamma Ray Space Telescope was launched in 2008, its mission to scan the entire sky for gamma rays, the most energetic form of light in the universe, often produced by the most violent events. For years, it dutifully collected its data, and to most observers, the gamma ray map of our galaxy looked as expected, a bright band across the sky corresponding to the Milky Way's disk. But a team led by astrophysicist Doug Finkbeiner looked closer. They knew this background emission was a kind of fog, and they worked meticulously to subtract it, to peel it back and see what lay beneath. What emerged from the data in 2010 left them stunned. Once the fog of diffuse gamma rays was cleared away, two immense, almost perfectly symmetrical structures came into sharp focus, ballooning out from the galactic center, one north and one south, like the wings of a cosmic angel or the aftermath of a titanic explosion frozen in time. The scale of these bubbles is humbling. Each one stretches for 25,000 light-years. That means from top to bottom, this structure is 50,000 light-years tall. Our entire solar system is a mere 27,000 light-years from the galactic center, placing us well within the shadow of this immense phenomenon. For an event to create such a vast, coherent structure, the energy required is almost beyond calculation. We are talking about the equivalent of millions of supernovae detonating in a relatively short period, a surge of power that must have fundamentally shaken the entire galaxy. The bubbles are not empty, they are filled with hot, magnetized gas that is emitting this high-energy light, and their edges are sharp, suggesting they are the result of a rapid, focused outburst rather than a slow, simmering process. This clarity of form is what makes them so mysterious. They are a distinct event written across the sky, a fossilized echo of a moment when the heart of the Milky Way roared. But what could have possibly created them? This is where the debate among astrophysicists becomes truly fascinating, centering on the two most powerful engines in any galaxy: star formation and its central black hole. The first leading theory points to a period of intense starburst activity at the galactic center. Imagine a sudden, ferocious wave of star birth, creating thousands of massive stars that lived fast, died young, and exploded as supernova almost simultaneously. The combined stellar winds and shock waves from all these explosions could have blown a gigantic bubble of hot gas out of the galactic disk in both directions, inflating these structures over millennia. The second, and perhaps more dramatic, theory implicates the supermassive black hole at our galaxy's core, Sagittarius, a star. While it is quiet today, it may not have always been so. This theory suggests that in the relatively recent past, Sagittarius, a star, awoke from its slumber as a vast amount of matter fell into its gravitational clutches. This feeding frenzy would have generated incredible energy, not just as light, but in the form of powerful jets of plasma and radiation shooting out along its poles. It is these jets punching through the galactic material that could have inflated the Fermi Bubbles like cosmic balloons. Doug Fink-Biener and his colleagues have pointed out the challenges with both scenarios. The sheer duration of the energy output needed to create and sustain such well-defined structures is a major puzzle. Was it a single, catastrophic explosion or a series of smaller outbursts? The evidence suggests the event that created the bubbles occurred somewhere between 2.5 and 4 million years ago, a mere blink in cosmic time. This leads to a profound and slightly unsettling implication. Our galaxy is not the stable, serene spiral we often imagine it to be. It may be subject to periodic eruptions, violent hiccups from its central engine that reshape its environment every few million years. This transforms our understanding of Earth's place in the cosmos. We are orbiting a star that travels through a galaxy with a volatile, explosive heart, and we may have, in our planet's deep history, already passed through the fading aftermath of such an event. This realization immediately prompts a new line of inquiry. If our galaxy has these structures, do others? Astronomers are now actively searching for similar Fermi-like bubbles in other spiral galaxies. Finding them would be a watershed moment, suggesting that such energetic outbursts are a common, perhaps even necessary, phase in a galaxy's life cycle. It could mean that black hole eruptions are not rare catastrophes but fundamental regulatory mechanisms, a way for a galaxy to vent excess energy, redistribute matter, and perhaps even quench star formation in its central regions. The Fermi Bubbles, therefore, are more than just a local mystery. They are a key to understanding galactic evolution itself. They show us that even the most familiar of cosmic settings can hold evidence of incredible violence, hidden in plain sight until we learned how to look. They are a reminder that sometimes the most startling discoveries are not made in the farthest reaches of the cosmos, but right in our own backyard, waiting for a curious mind to clear away the fog and see the magnificent structures lurking just beneath. From the explosive, energetic history of our own galaxy, we now turn our gaze outward to a structure of such serene and perfect beauty that it seems almost too flawless to be real. 600 million light-years away, in the constellation of Serpens, lies a cosmic jewel that defies simple explanation. Hoag's object, discovered in 1950 by astronomer Art Hoag, this galaxy appears as a stunning, almost perfect ring of brilliant blue young stars, encircling a core of older, yellower stars like a celestial halo. The most striking feature is the profound, dark gap that separates the two, a seemingly empty void of space that cleanly divides the ring from the core, creating an image of such symmetry and precision it looks less like a natural formation and more like a work of art. Hoag himself initially thought he was looking at a planetary nebula, the glowing shell of a dying star, but further analysis revealed the terrifying and wonderful truth. He was seeing an entire galaxy, and one that broke all the established rules. Typical galaxies come in familiar shapes, majestic spirals with curving arms, fuzzy ellipticals, or messy irregulars. Hoag's object fits none of these categories. It is the quintessential ring galaxy, but unlike others formed by violent collisions, like the Cartwheel Galaxy, which shows the chaotic aftermath of a direct impact, Hoag's object is isolated, serene, and unnervingly symmetrical. There is no sign of a second galaxy that could have punched through its center to create the ring, no debris trail of a cosmic accident. It simply exists in a state of pristine, solitary perfection, a cosmic eye staring back at us across the void. This profound isolation is the heart of the mystery. How does such a perfectly balanced structure form and, more importantly, maintain its incredible form over billions of years? The leading theories try to grapple with this, but each comes with its own challenges. One idea involves resonant dynamics, the concept that density waves, like a ripple in a pond, could have moved through the galaxy long ago, triggering a wave of star formation at a specific radius and creating that brilliant blue ring. Another possibility is a past accretion event, where a small, gas-rich dwarf galaxy was captured and torn apart by Hoag's object. As it was devoured, its gas could have been pulled into a stable orbit around the core, later collapsing to form the ring of new stars we see today. Yet, the utter lack of any remaining evidence for this dwarf galaxy makes this theory difficult to prove. What we are left with is a structure that appears both ancient and dynamic, a snapshot of a moment of cosmic equilibrium that has persisted for eons. The rarity of such objects only deepens the enigma. Despite decades of surveys, only a handful of true Hoag-type galaxies have ever been confirmed. This makes each one a precious natural laboratory for astrophysicists. By studying its rotation, the composition of its stars, and the delicate balance between its components, we can learn profound lessons about the forces of angular momentum, gravitational stability, and the life cycle of stars on a galactic scale. It challenges our models of how galaxies evolve without the need for dramatic collisions, suggesting that under the right, delicate conditions, a galaxy can sculpt itself into a form of breathtaking elegance. And it is that very elegance that inevitably leads the mind to wander into profound territory. Gazing upon the image of Hoag's object, one cannot help but feel a sense of awe that borders on the spiritual. Its perfect geometry feels intentional, designed. Of course, the scientific mind seeks natural processes, but the emotional response it triggers is a powerful reminder of why we look up in the first place. It represents a different kind of cosmic mystery, not one of violence and energy, but one of order and grace. It asks us to consider whether such perfection is a magnificent accident of physics or a hint of a deeper, more subtle order woven into the fabric of the universe. This celestial masterpiece, a perfect ring adrift in the blackness, sets the stage for our final and perhaps most perplexing mystery, one that moves from the beauty of a single structure to the unsettling suggestion of a pattern repeated across the cosmos itself. Yet for all the grandeur of galactic structures and the explosive history written across our own sky, perhaps the most haunting mystery in the search for cosmic company is not a vast, visible object, but a fleeting blip of data, a whisper from the void that lasted just 72 seconds and then vanished forever. This is the story of the WOW signal, An event so statistically improbable and so perfectly aligned with what we might expect from an artificial broadcast that it has become the white whale of modern astronomy. A single, tantalizing data point that continues to defy explanation and fuel our deepest hopes about not being alone in the universe. The tale begins in the pre-dawn hours of August 15, 1977, at the Big Ear Radio Telescope in Ohio. This was a workhorse instrument for the Search for Extraterrestrial Intelligence, or SETI, program, mechanically scanning the skies night after night, listening for any signal that stood out from the natural radio hiss of the cosmos. The data was printed out in rows of alphanumeric characters, each representing the intensity of a radio signal at a specific frequency. For days, it was a monotonous stream of numbers and letters, nothing but the expected background noise. But then, at 2:16 in the morning, the telescope's twin horns, pointed toward the constellation Sagittarius, recorded something extraordinary. The signal was not a smear of noise. It was a sharp, intense, and incredibly focused burst on the specific frequency of 1420 MHz. This is a profoundly significant frequency, known as the hydrogen line, because it's the natural radio wavelength emitted by neutral hydrogen, the most abundant element in the universe. Any technologically advanced civilization, the thinking goes, might use this universal, quiet channel as a clear, obvious place to broadcast a hello, knowing that any species with a radio telescope would be tuned to it. A few days later, a volunteer astronomer named Jerry Amon was poring over the reams of printout data. His job was to manually look for any anomalies, and as his eyes scanned across the page, he saw it. In a column, the sequence 6-5 leaped out. This wasn't random noise. This code represented a signal that rose dramatically in strength and then fell away, perfectly matching the expected profile of a narrowband signal passing through the telescope's fixed field of view as the Earth rotated. It was exactly what they had been hoping to find for years. Stunned by the sheer perfection of it, Amon took his famous red pen, circled the sequence, and wrote beside it a single, heartfelt word that would echo through history: "Wow." That exclamation of pure, astonished discovery has immortalized the signal, capturing the very moment a human being confronted something that seemed to defy all natural odds. And then the real mystery began. The search was on to find it again. If this was a deliberate broadcast from another star system, it should be repeatable. Astronomers pointed every available telescope they could back at that same patch of sky, listening on that same frequency, again and again and again. They scanned for decades. The result was a profound and, for many, a deeply frustrating silence. The wow signal never repeated, not once. It was a one-time event, a cosmic flash in the pan that has never been replicated, transforming it from a potential discovery into an enduring enigma. This failure to find a repeat is what elevates it from a curiosity to a profound puzzle. If it was a deliberate broadcast, why was it only sent once? Was it a targeted message that swept past us, a malfunctioning beacon, or was it something else entirely? This question has spawned a relentless search for a natural explanation, but each one has ultimately fallen short. One of the most discussed theories proposed that the signal might have been reflected radio emissions from one or two passing comets, whose hydrogen clouds could theoretically emit radiation near that frequency. However, this idea was thoroughly dismantled. The comets in question were not in the right part of the sky at that precise time, and the specific, intense, narrowband nature of the wow signal doesn't match the broad, diffuse radio signature a comet would produce. Other suggestions point to a terrestrial source, like a secret military transmission or a satellite passing overhead. But the unique characteristics of the Big Ear telescope make this incredibly unlikely. Its twin horn design meant a signal from Earth or a satellite would have appeared in both horns at slightly different times. The WOW signal appeared in only one, confirming it came from a fixed point in deep space. Even a bizarre atmospheric phenomenon, like a radio wave being bounced off a piece of space debris, fails to account for its perfect frequency and intensity profile. After nearly half a century, no natural explanation has stuck, leaving the door to possibility, however faint, still firmly ajar. The cultural and scientific impact of this 72-second event is immeasurable. It is the one incident in the history of SETI that cannot be easily dismissed. It is the ghost at the feast, the data point that proves the search is not in vain, that there might be something out there to find. It has inspired countless research proposals, dedicated listening campaigns, and has become a foundational story for a generation of astronomers. A reminder to always look twice, to never assume, and to keep a red pen handy for those moments when the universe seems to speak directly to us. It represents the ultimate what if, a question mark hanging over our species' lonely position in the cosmos. Ultimately, the power of the WOW signal lies not in what we know, but in what we don't. It forces us to confront profound questions about communication across the mind-boggling distances between stars. If it was a message, what could its purpose have been? A deliberate beacon aimed at the galaxy, an accidental leakage from a powerful civilization, or perhaps the final, dying transmission of a world long since gone silent. The silence that followed is just as meaningful as the signal itself. It is a lesson in cosmic patience and humility, reminding us that the universe operates on timescales far beyond our own. We may have simply been listening at the wrong time, our brief window of technological awareness missing the broader conversation happening over millions of years. The WOW signal is a solitary puzzle piece from a box we have not yet found, a single, brilliant note from a symphony we have only just begun to hear. It is a mystery that may never be solved, and in that uncertainty, it holds a permanent, powerful grip on our imagination, a brief shout into the darkness that, for one unforgettable moment, seemed like it might have been an answer. From the fleeting, tantalizing whisper of the WOW signal, we now journey to a mystery of an entirely different nature, not a momentary event, but a permanent, yawning chasm in the fabric of the cosmos itself. If the Hercules Corona Borealis Great Wall is a mountain range of unimaginable scale, then the void we are about to explore is its polar opposite. A canyon of nothingness so vast and profound it has earned the deeply unsettling nickname, the Great Nothing. Officially known as the Bootes Void, this region of space is not just empty. It is a staggering, almost violent absence of the things that should be there, a 700 million billion cubic light-year hole in the universe that defies our every expectation. Its discovery in the early 1980s was not a single eureka, a moment but a slow, dawning realization that something was deeply wrong with the map. Astronomers Robert Kirshner, August Oehmler, Paul Schechter, and Stephen Schechtman were conducting a large-scale redshift survey to chart the three-dimensional distribution of galaxies. As they pieced their data together, they found a region in the constellation of Bootes, the herdsman, that was alarmingly, unnervingly dark, where the cosmic web should have been a rich tapestry of galaxy clusters and filaments. There was instead a near-total void. Initial estimates suggested this cosmic desert was about 250 million light-years across, but later, more precise measurements have revealed its true, mind-numbing scale to be approximately 330 million light-years in diameter. To grasp the sheer immensity of this emptiness, consider that our entire local group of galaxies, which includes the Milky Way and Andromeda, is a mere 10 million light-years wide. You could fit over 30,000 of our local universes inside the Bootes void with room to spare. It is a volume of space so enormous that light, the fastest thing in the universe, would take more than 300 million years to cross from one side to the other, a journey through near total darkness. The true eeriness of the void, however, isn't just its size but its shocking emptiness. In a typical region of space that large, you would expect to find not thousands, not millions, but tens of thousands of galaxies. The Bootes void contains, by most recent counts, only about 60. That's 60 lonely islands in an ocean of nothingness that could comfortably hold 10,000. Astronomer Gregory Aldring, who has studied its peculiar galaxy distribution, once offered a perfect metaphor, saying, "If the Milky Way had been in the center of the Bootes void, we wouldn't have known there were other galaxies until the 1960s. This is the profound isolation we are talking about. The few galaxies that do exist within this great desert are not randomly scattered. They seem to be arranged in a tubular structure, as if huddling together for warmth in an impossibly cold and empty universe, a single, thin thread stretched across a cavern of nothing." This existence is a direct and formidable challenge to the lambda cold dark matter model, which is our best and most successful theory for how the universe evolved from the Big Bang to its current web-like structure. This model does predict voids. They are a natural result of gravity pulling matter into filaments and leaving behind emptier regions. But the voids it predicts are smaller, on the order of 50 to 100 million light-years across, and they are not truly empty. They should be webbed with faint filaments of dark matter and contain a sparse population of lonely, isolated galaxies. The Bootes void is an outlier of such extreme proportions that it forces cosmologists to ask a very difficult question. Is this just a statistical fluke, a 1 in a billion underdensity that our corner of the universe just happens to contain, or does it point to a fundamental flaw in our understanding of the universe's initial conditions? The theories attempting to explain its existence are as fascinating as the void itself. Some point back to the universe's infancy, to the period of inflation. Perhaps the void is a fossil, a preserved imprint of an enormous quantum fluctuation that occurred in the first fraction of a second after the Big Bang, a region where the density of the primordial universe was just slightly lower than its surroundings. Over 13.8 billion years of expansion, that tiny deficit was stretched into the colossal emptiness we see today. Others look to the mysterious force of dark energy, the enigmatic pressure causing the universe's expansion to accelerate. Could dark energy act more strongly in some regions than others, effectively pushing matter out of certain areas and sculpting these incredible voids? Then there are the more speculative, mind-bending ideas, such as the void being the scar of a collision with another universe in the multiverse, a bubble that brushed against our own and swept it clean in that region. What the Bootes void ultimately teaches us is that the universe is not just lumpy. It is a place of extreme textures with densities and emptinesses that push the very limits of physics. It is a humbling reminder that for all our mapping and modeling, the cosmos can still present us with structures so immense and counterintuitive that they feel less like natural formations and more like profound errors in the code of reality. It is the ultimate cosmic desert, a place where the rules seem different and the silence is deafening. This exploration of profound emptiness, however, now compels us to turn our attention back to the light, to the most crowded and energetic places in the universe, where galaxies don't hide but collide in spectacular displays of cosmic violence, creating environments so extreme they challenge our very definitions of life and possibility. But if the Bootes void represents a profound emptiness, a staggering absence of matter, then the next mystery presents us with the exact opposite. A universe that seems to be moving with a purpose, as if pulled by an unseen hand from a place we cannot see. We now venture into one of the most controversial and mind-expanding concepts in modern cosmology, a phenomenon so strange it has been dubbed the dark flow. Imagine the entire observable universe, all 93 billion light-years of it, expanding from the Big Bang in what should be a perfectly uniform and random fashion. Galaxies should be drifting apart like leaves on a pond with no preferred direction, yet that is not what some astronomers believe they have found. Instead, they point to evidence that thousands of massive galaxy clusters are all streaming in the same direction at incredible speeds, as if caught in a cosmic river whose source lies beyond the horizon of everything we can possibly observe. The detective work behind this astounding claim begins not with looking at the galaxies themselves, but by studying the oldest light in the universe, the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. It should be almost perfectly uniform, a canvas of subtle temperature variations that represent the seeds of all future structure. A team of astronomers led by Alexander Kashlinsky at NASA, a Goddard Space Flight Center, had a brilliant idea. They realized that if massive galaxy clusters were moving in a peculiar way, not with the general expansion of the universe, but with their own additional motion, they would leave a faint imprint on this ancient light through a process called the kinematic Sunyaev-Zeldovich effect. Essentially, as the hot electrons in these clusters plow through the CMB photons, they would scatter the light in a way that creates a very slight but measurable distortion in its temperature. It's an incredibly subtle signal, like trying to hear a single whisper in a roaring stadium, but by carefully analyzing data from the Wilkinson Microwave Anisotropy Probe, or WMAP, Kashlinsky's team believed they had found it. And the signal pointed to a coherent motion, a flow, on a scale that was utterly breathtaking. The numbers involved are enough to challenge one's sense of scale. This purported dark flow isn't a small, local current. The initial studies suggested that galaxy clusters were streaming at velocities of up to 1,000 kilometers per second toward a specific point in the sky between the constellations of Centaurus and Vela. Even more astonishing was the scale of this motion. It seemed to be detectable in clusters as far out as 3 billion light-years from Earth. This is a fundamental problem. According to the standard cosmological model, the influence of matter and gravity should be limited to the observable universe. There should be nothing beyond our cosmic horizon that could exert such a coherent pull on so much mass across such an immense volume of space. It would be like every ship in an ocean suddenly starting to sail in the same direction, pulled by a magnet located beyond the curve of the Earth itself. The very idea seems to violate the foundational principles of modern cosmology. This is why the dark flow remains one of the most hotly disputed topics in astrophysics. Skeptics have raised valid concerns, primarily that the measured signal is at the very edge of what our instruments can detect and could be contaminated by other foreground effects or systematic errors in the data analysis. Subsequent studies using data from the more advanced Planck satellite have failed to confirm the original findings with the same strength, though Kashlinsky and his collaborators maintain that their analysis still points to a residual, unexplained flow. The scientific community is therefore split, with many dismissing it as a statistical fluke or a measurement artifact, while others see it as a tantalizing, if unproven, clue to something far grander. For those who take the phenomenon seriously, the implications are nothing short of revolutionary. If the dark flow is real, it suggests that the distribution of matter in the universe is not uniform on the largest scales. It points to a gravitational anomaly of unimaginable proportions, something so massive and so distant that its tug is felt across billions of light years. What could possibly be powerful enough to do this? The most thrilling possibility is that the dark flow is evidence for the multiverse. In some models of inflationary cosmology, our universe is just one bubble in a vast, frothing sea of other universes. If another bubble universe happened to form extremely close to ours in the greater multiverse, its gravitational influence could, in theory, reach across the void and pull on the matter within our own cosmos. It's a concept that stretches the limits of physics, suggesting we are not just mapping our universe, but feeling the ghostly gravitational hand of a neighbor we can never actually see. Other exotic theories venture even further. In string theory and brain cosmology, our universe might be a three-dimensional membrane or brain floating in a higher dimensional space. The gravitational pull from another, nearby brain could potentially explain the coherent motion of the dark flow. Alternatively, it could be evidence of a pre-Big Bang structure, a relic from a time before our universe began, whose imprinted asymmetry still guides the motion of galaxies today. Each of these ideas is profoundly speculative, but that is the power of an anomaly like the dark flow. It forces us to consider possibilities that lie far outside the comfort zone of established science. Ultimately, whether the dark flow is confirmed or eventually dismissed, its value is undeniable. It represents the cutting edge of cosmology, a field that is constantly pushing against the boundaries of the observable and the knowable. It challenges the cosmological principle in a new and profound way, asking if we truly live in a homogeneous universe or if we are merely a small part of a much larger and far stranger structure. It encourages a humility about our place in the cosmos, reminding us that our view is limited to a finite sphere of light and time, and that beyond that horizon may lie realities and forces that we are only beginning to sense through their faint gravitational whispers. The dark flow is a mystery that points not to an object in the sky, but to a direction, a vector leading our gaze and our curiosity toward the ultimate question: what lies beyond the edge of everything we see? Yet for all the grandeur of these immense cosmic rivers and voids, some of the most breathtaking structures in the early universe are not defined by the absence of matter, but by its brilliant, luminous presence. Imagine a time when the cosmos was in its tumultuous adolescence, a mere 2 to 3 billion years after the Big Bang. In this ancient, formative era, astronomers have discovered something that defies even the violent norms of a young universe: colossal, glowing clouds of primordial gas, each one a cosmic ghost larger than an entire galaxy, shining with a mysterious internal light. These are the Lyman alpha blobs, and they are among the largest and most energetic single objects ever identified. Yet their power source remains one of the most captivating puzzles in modern astrophysics. The story of their discovery begins with a specific, telltale signature of light. Hydrogen, the most basic and abundant element in the universe, emits a very particular wavelength of ultraviolet light when it is energized, known as Lyman alpha radiation. For decades, astronomers used this signature to study individual, distant galaxies. But in the early 2000s, as our telescopes grew more powerful, they began to find something astonishing. Instead of compact points of light marking single galaxies, their surveys revealed enormous, diffuse clouds, some spanning 300,000 light-years or more, all glowing intensely with this same Lyman alpha emission. These were not sharp, defined objects. They were cosmic specters, vast and ethereal, like immense neon signs hanging in the void of the early universe. The first and most famous of these, discovered in the SSA-22 protocluster region, is so large that light would take hundreds of thousands of years to travel from one side to the other. A cloud of gas so immense it could easily swallow our entire local group of galaxies without a trace. The immediate, obvious question was, what could possibly make these gargantuan clouds of hydrogen gas shine so brightly? They are not hot enough to glow on their own like a star, so they must be illuminated by something incredibly powerful happening within them. The two leading natural explanations both point to cosmic violence on an epic scale. The first theory suggests these blobs are cosmic nurseries of unimaginable ferocity, regions where stars are being born at a rate hundreds or even thousands of times greater than in our own Milky Way. The combined ultraviolet output from all these massive, newborn stars would be staggering, flooding the surrounding cloud of primordial hydrogen with so much energy that it fluoresces, causing the entire gigantic structure to glow like a cosmic fluorescent bulb. The second theory points to the monstrous engine at the heart of a young galaxy, an active galactic nucleus or a quasar. This is a supermassive black hole in a frenzied feeding state, blasting out enough energy to outshine every star in its galaxy. The intense radiation from such a beacon could, in theory, travel for thousands of light years, lighting up a surrounding sea of gas and making it visible across the universe. However, as with all our deepest cosmic mysteries, the simplest explanations soon ran into problems. Some of these Lyman alpha blobs exhibit energies and characteristics that don't perfectly fit either model. The sheer size of the emission, the intricate structure within some blobs, and the precise way the light is distributed have led scientists to consider even more exotic possibilities. One compelling idea involves a process called cold accretion flow. This theory proposes that in the early universe, galaxies grew by drawing in vast, relatively cool rivers of hydrogen gas directly from the cosmic web. As this gas funnels down into the gravitational wells of protogalaxies, it can shock, heat up slightly, and produce the Lyman alpha glow we see, effectively tracing the invisible flow of matter that is building the galaxies themselves. In this scenario, the blob isn't just a cloud. It's a live action map of a galaxy under construction, a snapshot of cosmic nourishment on a scale we can barely comprehend. The significance of these enigmatic structures cannot be overstated. They are more than just beautiful cosmic oddities. They are vital time capsules. Because their light has traveled for over 10 billion years to reach us, they offer a direct window into the era of peak galaxy formation, allowing us to witness the processes that built the majestic structures we see in the mature universe today. By studying the dynamics within a blob, how the gas is moving, its density, and its temperature, astronomers can test their models of how gravity pulls matter together to form the galaxies and clusters we know. The SSA-22 blob, for instance, isn't alone. It sits at the heart of a dense knot of young galaxies, a protocluster that will one day evolve into a massive city of galaxies, and the blob itself may be the fuel source for this entire future metropolis. This leads us to the profound and lingering question at the heart of the Lyman alpha mystery. Are we looking at a single phenomenon or many? Is every blob powered by the same mechanism, or are we seeing a class of objects that share a common appearance but are lit by entirely different cosmic engines? Could some be stellar nurseries, others be illuminated by quasars, and still others be the visible manifestation of cold streams feeding a galaxy? The answer likely lies in a combination of these incredible forces, a symphony of cosmic creation where gravity, radiation, and matter interact in a complex dance. The Lyman alpha blobs stand as monumental beacons from the universe's youth, glowing testament to a time of frantic growth and incredible energy, and their faint, ancient light guides us toward an even more extreme and violent class of phenomena, where the energies involved make these colossal clouds seem almost placid by comparison. Yet for all the immense, glowing clouds of the early universe, Some of the most profound cosmic discoveries are not made in the distant past, but in our own time, and not by professional astronomers alone, but by hundreds of thousands of curious eyes scanning the digital sky. This brings us to one of the most charming and unexpectedly important discoveries of modern astronomy, the green pea galaxies. Their story begins not in a pristine observatory on a mountaintop, but at home on ordinary computers, where a global community of volunteer citizen scientists was given a monumental task to classify millions of galaxies from the Sloan Digital Sky Survey. The project was called Galaxy Zoo, and it was a revolutionary idea to harness human pattern recognition to tackle a data set too vast for any small team of researchers. And it was here, amidst this crowd-sourced cosmic census, that the peas were found. The name itself, coined by astronomer Carolyn Cardamon and her team, is a perfect fit, born from the comments of the volunteers themselves. As they sifted through image after image, they began to notice a few peculiar objects that didn't fit any known category. They weren't majestic spirals or fuzzy ellipticals. They were small, compact, and most distinctly they appeared as tiny, bright green dots against the blackness of space. In the false color images used by astronomers, this green hue was a specific signature, indicating an overwhelming intensity of light being emitted at a very particular wavelength. This was the telltale sign of highly energized oxygen gas, and it was shining brighter than anything else in these tiny galaxies. The volunteers, with their fresh, unbiased perspectives, had spotted something extraordinary that automated algorithms had missed, a new class of object that would soon become a critical key to understanding the universe's wild youth. But what exactly are these green peas, despite their small size, often only a few thousand light-years across, mere fractions of our Milky Way? They are absolute powerhouses of cosmic activity. They are factories of creation, forging new stars at a rate that puts nearly every other galaxy in the modern universe to shame. In a pea galaxy, stars are born hundreds of times faster than in our own home galaxy, a ferocious burst of stellar birth that floods the surrounding space with intense ultraviolet radiation. This radiation slams into clouds of primordial gas within the galaxy, exciting the oxygen atoms and causing them to fluoresce with that characteristic brilliant green glow. This same process is what makes planetary nebulae glow here in our own galaxy, but in the peas, it's happening on a galactic scale, turning the entire system into a dazzling cosmic neon sign. Their significance, however, goes far beyond their vibrant color and frantic star-making. These tiny galaxies are also cosmic relics, possessing extremely low metallicity. In astronomy, metals means any element heavier than hydrogen or helium. Since these heavier elements are forged in the hearts of stars and scattered by their explosive deaths, a low metal environment is a sign of a primitive, unspoiled system, one that has not yet been polluted by multiple generations of stars. This makes green pea galaxies the closest analogues we have to the first galaxies that lit up the infant universe. They are living fossils, offering us a nearby laboratory to study the processes that shaped cosmic evolution over 13 billion years ago during the epoch of reionization, the period when the first stars and galaxies burned away the cosmic fog of neutral hydrogen that filled the early universe. This connection to the ancient past is what makes them so invaluable to researchers. By studying the peas, we can test our theories about how those first galaxies heated and ionized their surroundings, fundamentally changing the nature of the cosmos. Astronomers like Cardamon have pointed out that the peas are so efficient at producing ionizing radiation that if they were common in the early universe, they could have been major players in this universal transformation. But this very efficiency also presents a new and tantalizing mystery. Why are these small galaxies so incredibly good at what they do? Observations show they are not alone. They often exist on the edges of larger voids or in loose groups, suggesting their environment plays a role in fueling their incredible star formation. Some theories propose that they are the result of recent galactic mergers, collisions that funneled vast amounts of fresh, pristine gas into a small volume, triggering an unstoppable starburst. Others look to their internal dynamics, where powerful stellar winds and supernova explosions from the first massive stars might actually compress nearby gas clouds, seeding the next wave of star birth in a powerful cycle of feedback. The story of the green pea galaxies is a powerful testament to the role of curiosity and collaboration in science. It proves that discovery is not the sole domain of experts with doctorates and access to giant telescopes. It shows that when the public is invited to participate, when hundreds of thousands of people are given the chance to explore, they can uncover hidden gems that change our understanding of the cosmos. These small, green, unassuming dots in the sky are a bridge, connecting the efforts of everyday people at their computers to the most fundamental questions about our universe's origin and evolution. They remind us that the cosmos is still full of surprises, and that sometimes the most important discoveries come in the smallest and greenest of packages. This journey from the macro to the micro, from vast voids to tiny, energetic galaxies, now compels us to widen our view once more, to examine the possibility of the largest structures of all, patterns woven into the very fabric of the cosmos on a scale so grand it challenges the limits of reality itself. But if the green pea galaxies show us the intense, small-scale fires of cosmic creation, then the Sloan Great Wall reveals the opposite extreme, the universe's grandest possible architecture, a structure so immense it seems to challenge the very rules of the cosmos. Discovered in 2003 by a team led by J. Richard Gott Roman III and Mario Jurek, this titanic formation emerged from the most ambitious map of the universe ever attempted at the time, the Sloan Digital Sky Survey. This project wasn't just looking at pretty pictures. It was using a specialized telescope to meticulously measure the redshifts and positions of millions of galaxies, effectively creating a three-dimensional atlas of the local universe. As this cosmic census data was pieced together, an astonishing pattern came into focus, not a random scattering of islands, but a continent. A vast, thread-like filament of superclusters, a web of gravity's influence made visible, stretching across an almost inconceivable 1.37 billion light-years from end to end. To even begin to grasp that scale, consider that a beam of light traveling from one end of this wall to the other would have begun its journey when the only life on Earth was single-celled microbes. This isn't just an object in space, it is a geographical feature of the cosmos, a mountain range on a universal scale. Its composition is what truly defines it. The Sloan Great Wall is not a solid, impenetrable barrier. That would be impossible given the vast emptiness between stars. Instead, it is a dense concentration of the cosmic web, a brilliant highway of interconnected superclusters, each one itself a sprawling metropolis of thousands of galaxies. These superclusters, with names like the Hercules supercluster, the Corona Borealis supercluster, and the Sloan Great Wall's own core, the massive Shapley concentration, are like the major nodal cities along this interstellar spine, linked by faint but detectable filaments of galaxies and dark matter. It is the ultimate expression of large-scale structure, a testament to how gravity, acting over billions of years, has pulled the universe's matter into a web of stunning complexity and order. Seeing its map is like looking at the neurological network of a cosmic brain, with galaxies for neurons and dark matter for the connecting tissue. and it is this very size and coherence that places the Sloan Great Wall directly at the center of a fundamental debate in modern cosmology. The structure stands as a direct challenge to the cosmological principle, the foundational assumption that, on the largest scales, the universe is homogeneous and isotropic. It should look roughly the same in every direction and from every location. There should be no grand centers, no edges, and certainly no structures that are exceptional or unique. A wall spanning well over 1 billion light-years seems to violate this principle spectacularly. It is an irregularity, a lump in the cosmic batter that is far larger than our best models of the Big Bang and subsequent inflation predict should be possible. The sheer statistical unlikelihood of such a feature existing in a truly random and uniform universe has forced cosmologists to confront a difficult choice. Is the wall a profound clue that our models are incomplete, or is it merely a once-in-a-universe fluke? This debate is at the heart of ongoing scientific inquiry. Some theorists, like astronomer Roger Clowes, who discovered the even larger Hercules corona Borealis Great Wall, argue that these structures, while immense, are still within the upper limits of what the standard lambda cold dark matter model can accommodate, if only just barely. They might be the result of a particularly large quantum fluctuation in the very early universe that was stretched to an epic scale during the period of rapid inflation. In this view, the Sloan Great Wall is a cosmic fossil, a preserved imprint of the universe's quantum origins. Others, however, see it as a more serious problem. The existence of such a wall and other comparable structures might suggest that inflation did not proceed in a perfectly uniform way, or that there are unknown forces or properties of dark energy and dark matter that can create these immense overdensities. It pushes our understanding of the universe's initial conditions to the breaking point. What does the persistent presence of such colossal walls reveal about the universe's true architecture? They suggest a cosmos that is not smooth and featureless but profoundly textured, with a complex geography of continents, oceans, and voids. This isn't a universe of random chaos, but one of emergent patterns where the simple law of gravity, given enough time and matter, can weave structures of breathtaking grandeur and scale. They hint that there may be deeper laws or initial conditions we have yet to fathom. Layers of order operating on scales we are only now becoming capable of observing. The ongoing quest to map the cosmos with even greater precision, using instruments like the James Webb Space Telescope and future redshift surveys, is essentially our attempt to read this cosmic geography, to understand whether the Sloan Great Wall is a rare masterpiece or a common feature of a universe far more structured and magnificent than we ever imagined. From the grand architecture of cosmic walls and the primordial glow of ancient blobs, we now turn our focus much closer to home, to an enigma that orbits our very own planet. A story woven from equal parts radiostatic, human imagination, and the cold, hard reality of space debris. This is the legend of the Black Knight satellite, a tale that begins not with a telescope, but with one of history's greatest electrical minds listening to the stars. In the early 20th century, Nikola Tesla was conducting pioneering experiments with his high-powered radio transmitter in Colorado Springs. During these tests, he reported receiving a strange, repeating signal, a series of rhythmic clicks that he speculated could be an attempt at communication from another world, perhaps even Mars. While modern analysis suggests Tesla was likely detecting natural pulsars or even unintentional interference from his own equipment, his account planted a powerful seed, the idea that something artificial might already be circling our world, watching and waiting. The story truly took flight decades later, in the 1950s, when various news outlets and aviation magazines reported that the U.S. Air Force had detected a mysterious, dark object in polar orbit, a type of orbit that was unusual and considered strategically valuable at the time. These reports, often based on speculation and the anxieties of the early space race, were quickly seized upon by UFO enthusiasts. The narrative coalesced around the idea of an ancient alien probe, dubbed the Black Knight, silently tracking human civilization for millennia. The legend was supercharged in 1998 when the Space Shuttle Endeavour mission STS-88 captured photographs of a strange, irregular object during a flight to the nascent International Space Station. The image, widely circulated online, showed a dark, jagged shape against the backdrop of Earth, and for many, this was the long-awaited photographic proof. The Black Knight had finally revealed itself, but what does science have to say about this compelling narrative? The evidence, when examined critically, points not to an extraterrestrial artifact, but to a series of perfectly ordinary, if misunderstood, human-made objects and natural events. The object in the famous Endeavour photograph, for instance, has been conclusively identified as a thermal blanket lost during an earlier spacewalk. These blankets, used to protect equipment from temperature extremes, are often large, crinkled, and highly reflective, making them appear bizarre and artificial when tumbling through the void. As for the unusual orbital detections from the 50s, these are almost certainly accounts of early spy satellite tests or discarded rocket boosters from the superpowers' frantic launch schedules, objects that were highly classified at the time and thus ripe for misinterpretation. The most persistent element of the myth, the repeating radio signal, also has a far more grounded explanation. In the 1920s, long-distance radio communication often relied on long-delay echoes, where a broadcast would bounce between the Earth's ionosphere and the ground, returning seconds later and creating an eerie echo. While not fully explained even today, these echoes are a recognized atmospheric phenomenon, not an alien broadcast. The human brain is a powerful pattern recognition engine, and it is wired to find meaning in randomness, to see faces in clouds and hear voices in static. The Black Knight is a perfect example of this apophenia, where unrelated data points, Tesla's experiment, Air Force rumors, a lost piece of equipment, are woven together into a coherent and thrilling story that satisfies a deep-seated need for mystery. And that, perhaps, is the true power and enduring appeal of the Black Knight satellite. It is less about astronomy and more about mythology. It taps directly into the ancient astronaut trope, the tantalizing idea that evidence of alien visitors is all around us, hidden in plain sight by governments and only visible to those who are willing to question official narratives. This legend and others like it fulfill a profound human desire to believe that we are not alone and that our history is far more spectacular than the textbooks tell us. They represent a form of modern folklore, a space-age campfire story that thrives in the digital age, passed from person to person through forums and videos. While critical thinking and a respect for evidence are essential tools for navigating these stories, we can also appreciate the cultural phenomenon they represent, a testament to our boundless curiosity and our timeless fascination with the stars above. This journey from myth to reality prepares us to examine a final, far more substantial cosmic puzzle, one supported by hard data and observed by astronomers worldwide, a true anomaly that resides in the distant depths of intergalactic space. But what if the true signature of an advanced civilization isn't a deliberate signal or a fleeting radio burst, but something far grander, a fundamental restructuring of its environment on a scale that alters the very light of its star? This brings us to one of the most captivating and controversial ideas in modern astronomy, the megastructure hypothesis, a concept that leapt from the pages of science fiction into scientific discourse, thanks to the baffling behavior of a single, unassuming star 1400 light-years away. Known officially as KIC 8462852, but forever immortalized as Tabby's star after its discoverer, Tabitha Boyajian, this object became a global sensation not for what it added to the cosmos, but for what it seemingly took away. The Kepler Space Telescope, designed to find planets by the gentle, periodic dimming they cause as they transit their stars, found something utterly different here. Instead of the telltale, repeating dip of a planet, Kepler observed drastic, irregular drops in the star's light plunges of up to 22% that could last for days and then vanish, with no discernible pattern or rhythm. It was as if something enormous, something unlike any natural object we knew, was sporadically blocking the light in a way that defied all conventional explanation. The immediate scientific reaction was a frantic search for a natural culprit. Could it be a vast, swirling cloud of dust and debris, perhaps the aftermath of a catastrophic planetary collision? Maybe a huge swarm of giant comets, thousands of them, passing in front of the star in a chaotic procession, or even intrinsic stellar activity of a kind we'd never witnessed, with massive starspots causing the dimming. Astronomer Tabitha Boyajian, who led the initial analysis, meticulously investigated these possibilities. As she and her colleagues noted, each natural explanation faced significant hurdles. A dust cloud would likely irradiate the absorbed energy as infrared heat, but follow-up observations showed a puzzling lack of excess infrared radiation. A cometary swarm would need to be impossibly large and dense to cause such deep dimming events. The mystery only deepened, leaving a vacuum that was quickly filled by a more extraordinary idea. Penn State astronomer Jason Wright offered a provocative alternative. What if we were seeing the shadows of something artificial? He suggested the dimming pattern was consistent with a vast, incomplete array of orbiting solar collectors, a megastructure in the process of being built, perhaps the beginnings of a Dyson sphere, a hypothetical shell or swarm of objects designed by a Type II civilization to harness the entire energy output of its star. The cultural and scientific impact of this hypothesis was electric. It revitalized the search for extraterrestrial intelligence, or SETI, shifting its focus from listening for radio signals to searching for these so-called technosignatures, physical evidence of astroengineering on a staggering scale. The public imagination was instantly captured. Here was a mystery that felt ripped from a blockbuster film, playing out in real data from a NASA mission. Telescopes around the world, from the amateur networks of the American Association of Variable Star Observers to the mighty Green Bank Telescope, were hastily aimed at Tabby's star, searching for any further clues, be they laser pulses, radio transmissions, or more dimming events. For a thrilling moment, it felt like humanity was on the precipice of an epochal discovery. Jason Wright himself captured the careful balance of this scientific pursuit, stating, "I was fascinated by how crazy it looked. Aliens should always be the very last hypothesis you consider, but this looked like something you would expect an alien civilization to build." This ethos of open-minded, rigorous investigation without premature conclusion became the guiding principle. Subsequent, more detailed observations have since tilted the weight of evidence back toward a natural, albeit still unusual, explanation. Extensive monitoring, largely funded by a massively successful public Kickstarter campaign, revealed that the star dims differently at different wavelengths of light. This is a key diagnostic. A solid, opaque object like a megastructure would block all colors of light equally, while fine dust scatters blue light more effectively than red. The observed chromatic dimming strongly suggests that whatever is blocking the light is likely a cloud of microscopic dust grains, finer than particles of cigarette smoke. The prevailing theory now is that Tabby's star is surrounded by a chaotic, uneven disk of dust, perhaps ejected from a disrupted moon or planet, creating a dynamic and evolving veil that causes the bizarre dimming patterns. While this solves the immediate mystery, the legacy of Tabby's star is far more profound than a single solution. It forced astronomers to seriously consider and develop the tools to search for technosignatures, transforming a fringe concept into a legitimate field of study. It demonstrated the power of citizen science and public engagement in funding and advancing cutting-edge research. And most importantly, it permanently expanded the toolkit for the search for life, reminding us that other intelligences might not be signaling us with radios, but might instead be revealed by the shadows their cosmic ambitions cast upon their suns. This pursuit of shadows now leads us to an even more profound and ancient shadow, a cosmic event so immense and destructive that its true nature remains one of the greatest unsolved puzzles in the history of our universe. Yet for all the immense and isolated structures we've explored, from voids to walls, they are not separate anomalies but rather integral parts of a single, breathtakingly vast architecture that binds the entire cosmos together. This is the cosmic web, the fundamental skeleton of the universe, an intricate network of dark matter filaments and galaxy clusters weaving through the emptiness, forming the largest pattern in all of existence. To truly grasp its scale is to attempt to hold infinity in your mind. Imagine a sponge of such immense proportions that its solid strands are each made of thousands of galaxies, and its holes are voids so large they could swallow universes. This is not a static sculpture but a dynamic, living structure, a cosmic dance choreographed by gravity over 13.8 billion years, and it is the stage upon which every galaxy, every star, and every planet has come into being. The story of its discovery is a triumph of both theory and observation, a perfect marriage of what we can predict and what we can see. For centuries, astronomers mapped the heavens in 2 dimensions, seeing only a flat tapestry of stars. It wasn't until we learned to measure the redshift of galaxies, the stretching of their light as they move away from us, that we could construct a true 3-dimensional map of our local universe. When the first large-scale surveys, like the Sloan Digital Sky Survey, began to plot the positions of millions of galaxies, the result was not the random, splattered distribution many had expected. Instead, a pattern emerged from the chaos, revealing a delicate, lace-like structure of connected filaments and colossal voids. This observed reality was stunningly predicted by supercomputer simulations of the universe's evolution, which showed how the invisible gravitational pull of dark matter, the universe's hidden scaffolding, would inevitably draw normal matter into this specific web-like pattern. What we see with our telescopes is the luminous trace of galaxies, tracing out the shape of an invisible dark matter skeleton we cannot see directly. To make sense of this structure, we need a relatable analogy. Picture the universe as a global brain. In this model, the dark matter filaments are the axons and dendrites, the long, thin pathways that form the connections. The dense clusters of galaxies where these filaments intersect are the neurons, the nodal points of immense activity and energy, and the vast, empty voids between them are the silent spaces, the resting state from which activity emerges. Another powerful image is that of a colossal spider's web, spun on a scale beyond human comprehension, glistening with dewdrops that are entire galactic superclusters. These analogies are more than just poetic. They help us conceptualize a network where gravity is the fundamental force of connection, pulling matter into rivers and nodes, creating a universe that is structured and organized, not random and formless. But for all its grandeur, the cosmic web is not fully understood. It presents us with profound and active mysteries that are at the very frontier of cosmology. We still do not know the precise nature of the dark matter that forms its backbone, nor do we fully understand the role of dark energy, the repulsive force that is now accelerating the expansion of the universe. Is dark energy subtly influencing the web's growth, perhaps stretching the filaments thinner or preventing new structures from forming? The formation of the web's densest nodes, the galaxy clusters, is another area of intense research, as scientists work to understand the complex physics of how gas cools, stars form, and black holes feed back energy within these crowded metropolitan centers of the cosmos. Each of these questions is a thread in a larger investigation, pulling us closer to understanding the universe's past and its ultimate fate. Contemplating this grand design is to engage in the ultimate act of cosmic perspective. Every single thing we know and are is part of this web. Our Milky Way galaxy is not floating in isolation. It is a single speck of light on a single strand of this universal tapestry, a tiny part of the Laniakea supercluster, which is itself just one local knot in the immeasurably larger pattern. This realization connects the vast to the intimate, showing how the immense gravitational tides of the cosmic web influenced the very cloud of gas that collapsed to form our sun and our planet. It is a humbling and awe-inspiring thought that we, conscious beings on a tiny world, can not only perceive this magnificent structure, but can begin to understand the laws that shaped it. This grand architecture, with its beautiful and mysterious filaments, now leads us to examine specific, strange threads within it, anomalous structures woven into the web itself that challenge our understanding of its very design. But as we map the grand cosmic web and its luminous nodes, we must also turn our attention to the most ancient light of all, a relic from the very dawn of time that holds its own set of profound and unsettling imperfections. This brings us to a chill in the cosmic background, a mysterious cold place that should not exist. Imagine the universe as a newborn, just 380,000 years old, emitting its first burst of light after the fiery chaos of the Big Bang had cooled enough for atoms to form. This light, now cooled and stretched by 13.8 billion years of expansion, fills the entire sky as a nearly uniform glow, the cosmic microwave background. It is the universe's baby picture, and like any photograph, it has a few unexpected smudges. Among them, one stands out for its sheer size and profound coldness, a region in the constellation Eridanus that is significantly cooler than the average, a vast and enigmatic patch of shadow on the first light of creation known simply as the cold spot. The discovery of this anomaly is a story of ever-increasing precision in our cosmic cartography. It was first tentatively identified in data from the Wilkinson Microwave Anisotropy Probe, or WMAP, in 2004. But it was the Planck satellite, launched in 2009 with vastly superior instruments, that confirmed its existence with stunning clarity. Planck's all-sky map of the CMB is the most detailed we have, a mottled tapestry of tiny temperature fluctuations that represent the seeds of all future structure, the galaxies and voids we see today. Most of these fluctuations are minuscule, varying by mere millionths of a degree. The cold spot, however, is a giant. It spans a staggering 1 billion light-years across, a colossal imprint on the sky, and its temperature is a profound 70 microkelvins colder than its surroundings. According to our standard models of cosmic inflation, which predict a generally uniform distribution of these primordial fluctuations, a feature this large and this cold is incredibly unlikely, a statistical outlier that pushes the boundaries of what randomness can produce. So what could have cast such a vast shadow on the dawn of time? Astronomers have put forward two competing classes of explanation, one that seeks an answer within the known universe and another that ventures into the profoundly speculative. The leading in-universe theory proposes that the cold spot is not a feature of the primordial CMB at all, but rather a later illusion, a shadow cast by a tremendous void between us and the ancient light. This is known as the integrated Sachs-Wolfe effect. The theory goes that if a photon from the CMB passes through a region of significantly underdense space, a huge void, it must climb out of a gravitational well that is becoming shallower due to the accelerating expansion of the universe driven by dark energy. This process costs the photon a tiny amount of energy, causing it to appear slightly cooler or redshifted when it finally reaches our telescopes. If a supervoid, an enormous emptiness on par with the Boötes void, exists along our line of sight to the cold spot, it could theoretically create this chilling effect. The hunt for this proposed supervoid has been intense. Some surveys have indeed found evidence of a large underdensity of galaxies in that direction, but the debate rages on whether this void is truly large enough and empty enough to account for the entire cold spot effect. For many cosmologists, the numbers simply don't add up. The observed void seems too insignificant to explain the profound cold. This failure of a conventional explanation is what opens the door to breathtakingly exotic possibilities, most notably the idea that the cold spot is evidence for the multiverse. This radical theory, championed by theoretical physicist Laura Mersini-Houghton, suggests that the cold spot is a cosmic bruise, the imprint of a collision between our universe and another bubble universe in a vast multiverse. In the eternal inflation model, our universe is just one bubble in a foaming sea of universes, each with its own physical laws. According to Mersini-Houghton's calculations, if our young, inflating universe had brushed against a neighboring bubble, the interaction would have drained energy from that region of our cosmos, leaving behind a distinct cold imprint in the CMB. She predicted the general size and location of such an anomaly before the WMAP data was fully analyzed, and the subsequent discovery of the cold spot in that very region was, for her and her colleagues, a stunning validation. Of course, this remains a highly controversial claim, with many physicists arguing that such an interpretation is premature and that unknown aspects of inflation or dark energy could yet provide an answer without invoking other universes. The cold spot, therefore, is far more than a curious blemish on a map. It is a critical battleground for our understanding of reality itself. It tests the limits of inflationary cosmology, pushing it to its breaking point and demanding either a refinement of the theory or a leap into a breathtaking new paradigm. It forces us to ask if the largest anomalies we see are simply cosmic defects, statistical flukes in an otherwise orderly process, or if they are something far more significant, windows into other dimensions, glimpses of a grander multiversal structure, or clues to a physics that operates beyond the confines of our single universe. This cold, silent patch of sky challenges us to decide whether our universe is a solitary island of reality or just one page in an infinite cosmic library, and its enduring mystery ensures that our gaze will remain fixed on this ancient shadow, searching for the truth it holds about the nature of everything. Yet the most profound implication of this galactic ring extends far beyond the mechanics of its formation, reaching into the invisible realm that governs all cosmic structures, the mysterious distribution of dark matter. Our entire understanding of how galaxies form and are held together rests upon the gravitational scaffolding provided by dark matter halos. These vast, invisible spheres of unknown particles are thought to envelop every galaxy, their gravity dictating the motion of everything within them. The existence of the Ring of Galaxies presents a direct challenge to the standard model of this dark matter cosmology, known as the lambda cold dark matter model. This model predicts that smaller satellite galaxies, the dwarfs that make up the ring, should be accreted randomly over time from all directions, falling into the Milky Way's halo and ending up in a roughly spherical, disordered cloud around us. The precise, co-rotating plane we observe is a glaring anomaly. It suggests that the dark matter halo itself may not be the simple, fluffy sphere we imagine. Perhaps it has a distinct substructure, a preferred plane, or a historical anisotropy that funneled these incoming galaxies into a specific alignment. Or, even more radically, it might hint that our very understanding of how dark matter behaves, its interactions and properties, is incomplete. Could certain dark matter theories, like those involving warm dark matter or self-interacting particles, better explain how such a thin, coherent structure could form and persist? The ring is more than a collection of stars. It is a cosmic probe, using the motion of visible galaxies to interrogate the nature of the invisible universe. This local mystery connects to a far grander cosmological puzzle, one observed not just around our galaxy but throughout the universe. Astronomers like Noam Libeskind and Marcel Poloski have been at the forefront of studying these structures, noting that such vast, coherent planes of satellite galaxies are not unique to the local group. Surprisingly thin and rotating arrangements of dwarf galaxies have been spotted around our neighbor, the Andromeda Galaxy, and even around more distant galaxies. This suggests that the phenomenon we see in our backyard might be a common yet unexplained feature of galactic evolution. The existence of these satellite planes forces a fundamental question. Is the standard model of cosmology in need of a significant revision, or are we witnessing the complex and subtle fingerprints of the cosmic web itself influencing local dynamics? The same dark matter filaments that weave the large-scale structure of the universe might be guiding smaller galaxies into preferred pathways as they flow into the gravitational wells of larger ones like our own. The ring of galaxies, therefore, transforms from a local curiosity into a critical data point in a much larger debate. It represents a tension between the top-down influence of the cosmic web and the bottom-up process of random accretion, a tension that current simulations struggle to resolve. Contemplating this magnificent, silent ring invites a moment of profound perspective. We reside within the very structure we are trying to decipher, on a planet orbiting a star in a galaxy that is itself the central anchor of this mysterious cosmic carousel. The ordered beauty of this arrangement, a graceful dance of galaxies on a scale of millions of light-years, is a humbling reminder that the universe expresses patterns and symmetries at every scale, from the quantum to the cosmic. It challenges the notion that the closer we look, the more chaotic things become. Sometimes, the closer we look, the more we find an elegant, if baffling, order. This ring is not a static monument but a dynamic, evolving relic of our local universe's history, a history written in the orbits of these tiny, ancient galaxies. Its continued study promises to unlock secrets not just about our own galactic home, but about the fundamental laws that shaped all galaxies from the dawn of time. As we push our telescopes to their limits, peering into the deep fields of space, we carry the lessons learned from this nearby ring, using them to interpret the even more magnificent and mysterious structures that lie in the unimaginable vastness beyond our local group of galaxies. But as we map the grand cosmic web and its luminous nodes, we must also turn our attention to a fundamental accounting error on a universal scale, a case of missing matter that has forced astronomers to become cosmic detectives. This is the mystery of the missing baryons. Baryons are the building blocks of the familiar world protons and neutrons that make up everything we can see and touch, from stars and planets to our own bodies. According to our most precise measurements of the early universe, specifically from the cosmic microwave background, we have a very accurate ledger of how much of this ordinary matter should have been created in the Big Bang. Yet, when we take a census of the present-day universe, adding up all the matter in stars, galaxies, and the detectable gas clouds between them, we come up dramatically short. Nearly half of all the baryons that should be here are simply unaccounted for. It's as if the universe's inventory list says a warehouse should be full, but when we open the doors, half the shelves are empty. This puzzle didn't emerge from a single failed observation, but from a slow, dawning realization as our cosmic accounting methods improved. For decades, cosmologists trusted that the matter we could see in galaxies was most of what existed. But as computer simulations of the universe's evolution grew more sophisticated, they painted a very different picture. These models, which trace the growth of structure from the smooth early universe to the web we see today, consistently showed that the vast majority of ordinary matter shouldn't be locked up in galaxies at all. Instead, it should be spread throughout the intergalactic voids, woven into the filaments of the cosmic web itself. The problem was, this predicted matter was in a form we had no way to see, a diffuse, superheated plasma too thin to emit light and too hot to absorb it in ways our telescopes were designed to detect. The universe, it seemed, had hidden most of its ordinary matter in plain sight. The prime suspect for this hiding place is a theorized phenomenon with a wonderfully evocative name, the warm-hot intergalactic medium, or WIM. This is not a dense, cold cloud of gas, but a tenuous million-degree plasma that exists in the vast filaments connecting galaxy clusters. Finding it is a monumental challenge. Because it's so diffuse, it doesn't glow brightly enough to be seen directly. Instead, astronomers have to look for its ghostly signature indirectly, using the most powerful space telescopes tuned to specific wavelengths. The strategy is to use distant, incredibly bright objects like quasars as cosmic flashlights. As the light from a quasar travels billions of light years to reach us, it passes through these invisible filaments of the WIM. Atoms within the hot gas, like oxygen and nitrogen, absorb very specific wavelengths of this brilliant background light. The Hubble Space Telescope's Cosmic Origin Spectrograph, or COSS, was specifically designed for this painstaking work, acting like a forensic chemist analyzing the light for the telltale absorption lines that prove the presence of these elusive elements. It's a bit like trying to detect a specific kind of fog by studying how it dims the color of a faraway street lamp. The hunt doesn't end with ultraviolet light. X-ray telescopes like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton are also on the case, searching for the faint glow this million-degree gas should emit at much higher energies. Recent years have seen tantalizing breakthroughs, with teams claiming to have detected the WIM by stacking countless X-ray observations along the lines of sight to distant galaxy clusters, finally teasing out a signal from the noise. These discoveries are beginning to close the gap in the cosmic ledger, suggesting that the missing baryons aren't truly missing, they've just been masquerading as an almost invisible fog, filling the spaces between the galaxies. Solving this mystery does more than just balance the books. It provides a crucial piece of the puzzle for understanding how galaxies themselves evolve. This reservoir of hot, intergalactic gas is the universe's main supply of fuel for future star formation. Galaxies are not closed systems. They are constantly accreting matter from this surrounding medium, and the properties of the WIM dictate how this process works. Furthermore, the effort to find these missing baryons has profoundly humbled us, demonstrating that even the ordinary matter we thought we understood can evade our detection if it's in the wrong state. This immediately raises a more profound question. If we have so much trouble finding the ordinary matter we know must be there, what does that say about our ability to detect the truly exotic components of the universe, like dark matter and dark energy, which by their very nature don't interact with light at all? The search for the missing baryons is a masterclass in cosmic humility. proving that the universe is still full of secrets, even in its most fundamental ingredients. But if the cold spot represents a single, chilling imperfection in the universe's first light, then the next anomaly we must confront is far more comprehensive, a pattern of alignment so unsettling it was given a name straight from a thriller, the axis of evil. This is not a localized cold patch, but a series of large-scale correlations in the cosmic microwave background that seem to point in a specific direction, suggesting the cosmos might have a built-in sense of orientation, a fundamental bias that runs directly counter to our most cherished cosmological principle. The very foundation of modern cosmology rests on the assumption of isotropy, the idea that the universe has no preferred direction, no special center, and looks the same in all directions from any vantage point. The axis of evil, if it is real and not a grand illusion, doesn't just challenge this idea, it threatens to pull the rug out from under it. The story of its discovery and naming is a perfect blend of scientific rigor and dark humor. As data from the Wilkinson Microwave Anisotropy Probe, or WMAP, was analyzed in the early 2000s, astronomers began to notice strange, large-scale patterns. The fluctuations in the CMB weren't entirely random. Certain modes of these fluctuations, particularly the quadrupole and octupole moments which describe the largest possible waves on the sky, appeared to be aligned with each other. Even more bizarrely, this alignment also seemed to be correlated with the plane of our own solar system and the direction of our motion through the cosmos. It was as if the universe's oldest light was somehow aware of our local, insignificant neighborhood. In 2005, researchers Kate Land and Joe Megiddo, grappling with the deeply unsettling implications of this finding, coined the provocative term axis of evil to describe it. The name stuck not because they believed it was literally evil, but because it so perfectly captured the threat this alignment posed to the standard, isotropic model of the universe. It was the perfect villain for our cosmological story. The potential explanations for this eerie alignment fall into two broad, deeply opposing categories. The first, and for many scientists the most comforting, is that it is a colossal systematic error. Perhaps it is an artifact of the way we process the WMAP and Planck data, an unintentional bias introduced when we subtract the foreground emission from our own galaxy. The Milky Way's bright disk blazes across the center of the CMB map, and meticulously cleaning this contamination from the ancient signal is an incredibly complex task. It is entirely possible that a slight imperfection in this cleaning process could leave behind residual patterns that mimic a large-scale alignment. Other proposals suggest it could be the effect of gravitational lensing, where the gravity of nearby galaxy clusters subtly distorts the CMB light on its way to us, though most models suggest this effect would be too weak to create the observed signal. If the axis is merely a data processing ghost, it would be a monumental relief to cosmologists, preserving the sanctity of the cosmological principle. However, if follow-up observations and more precise data from future missions continue to confirm its existence, then we are forced to venture into the realm of spectacularly new physics. Some theorists have proposed that the axis of evil could be evidence that the entire universe is rotating, a concept that would require a complete overhaul of general relativity and our understanding of angular momentum on a cosmic scale. Others have looked to the idea of a pre-Big Bang universe, suggesting that the alignment is a fossilized imprint of a prior state of existence, a structure or a directionality that survived the birth of our cosmos. Perhaps the most profound possibility is that the universe is not infinite and isotropic, but finite and topologically complex, like a hall of mirrors. In such a universe, light could wrap around, creating repeating patterns and correlations that make it appear as though there is a preferred direction, when in fact we are just seeing the same structure from different angles. Each of these ideas is radical, pushing the boundaries of known physics and forcing us to consider that our universe might be far stranger and more structured than we ever imagined. The controversy surrounding the axis of evil is a masterclass in how science grapples with profound anomalies. For every paper presenting evidence of the alignment, there is another offering a meticulous statistical argument that the effect is not significant, that it is simply a fluke of chance in a vast and complex data set. This healthy skepticism is the engine of scientific progress. The axis of evil has not been accepted as fact, but it has not been dismissed either. It persists as a nagging question, a persistent outlier that compels cosmologists to double-check their work, to refine their models, and to remain open to the possibility of a paradigm shift. It embodies a critical lesson that our most fundamental assumptions must always be subject to interrogation by the data, no matter how uncomfortable that interrogation might be. Ultimately, the axis of evil invites a profound philosophical reflection on directionality and our place in the cosmos. For centuries, we have moved away from the idea that we occupy a special place in the universe, embracing the Copernican principle that we are nowhere special. The axis of evil subtly turns this on its head. The alignment with our solar system could be the ultimate cosmic coincidence, a 1 in a billion fluke. Or it could be a deeply unsettling hint that we are, in some way we do not yet understand, connected to the largest scale structures of the universe. It asks us to consider whether the cosmos has an inherent geometry, a cosmic north that influences the formation of everything within it. This contemplation of a universe with a built-in axis naturally draws our gaze outward, to see if this apparent preference for alignment is merely a ghost in our oldest light, or if it is echoed in the architecture of the universe's most magnificent and recent structures. Yet for all the large-scale alignments and ancient shadows we've mapped, some of the most compelling cosmic mysteries are not written in the subtle patterns of ancient light, but in the violent, high-energy radiation that screams from the heart of our own galaxy. This brings us to a puzzle that has captivated and divided astrophysicists for over a decade, a case of too much of a good thing emanating from the most chaotic place in our celestial neighborhood. It's known as the galactic center excess, and it is exactly what it sounds like, a baffling, unexpected surplus of gamma-ray light, the most energetic form of light in the universe pouring from the core of the Milky Way. It's a signal that shouldn't be there according to our best models of known astrophysical objects, a brilliant and enigmatic glow that has sparked one of the most intense detective stories in modern science, a story where the chief suspect is the most elusive substance in the cosmos, dark matter. The detective in this story is the Fermi Gamma Ray Space Telescope, specifically its Large Area Telescope, or LAT instrument. Since its launch in 2008, Fermi has been tirelessly scanning the entire sky, building up the most detailed map ever made of the universe in gamma rays. When scientists began to analyze the data pouring in from the galactic center, they expected to see a lot of action. This region is a known cosmic zoo, packed with pulsars, supernova remnants, and the intense radiation from materials swirling around our supermassive black hole, Sagittarius A star. They carefully modeled all these known sources of gamma rays and subtracted them from the map, expecting to be left with a smooth, featureless background. Instead, they found something astonishing. A persistent residual glow of gamma-ray emission, roughly spherical in shape and extending thousands of light years from the core. It was as if they had carefully accounted for every known instrument in an orchestra, only to still hear the clear, distinct sound of a mysterious new instrument playing along. The immediate and most thrilling hypothesis was that this excess glow was the long-sought signature of dark matter annihilation. The theory is elegant. If dark matter is made of weakly interacting massive particles, or WIMP, as many physicists believe, then these particles could be their own antimatter counterparts. Where dark matter is most densely concentrated, like in the heart of galaxies, these particles could occasionally collide and annihilate each other, converting their mass directly into energy and producing a shower of secondary particles, including gamma rays at a very specific energy. The galactic center, with its immense gravitational pull, is thought to be the densest cloud of dark matter in the entire Milky Way, making it the perfect place to look for this telltale signal. The observed characteristics of the galactic center excess, its smooth, symmetrical shape and its specific energy spectrum, matched surprisingly well with the predictions for annihilation from a WIMP with a mass around 30 to 40 gigaelectronvolts. For a moment, it seemed like Fermi might have accidentally stumbled upon the first direct, non-gravitational evidence of dark matter, a discovery that would undoubtedly warrant a Nobel Prize. But extraordinary claims require extraordinary evidence, and the scientific community mobilized to find a more mundane explanation. The leading alternative theory is that the excess is not from dark matter at all, but from a vast population of previously undetected millisecond pulsars. These are ancient, rapidly spinning neutron stars that have been spun up by accreting material from a companion star, and they beam out powerful jets of radiation that sweep across space like a lighthouse. Because they are old and faint, thousands of them could be hiding in the crowded stellar fields of the galactic center, each one contributing a tiny amount of gamma radiation that, when added together, creates the smooth, diffuse glow we see. The challenge is that at such a great distance, Fermi's LHT cannot resolve individual point sources that are this faint. They all blur together into what appears to be a single, smooth emission. It's like looking at a city from a great distance at night. You see a general glow, but you can't make out the individual streetlights that create it. This is where the debate stands today, a fascinating tug of war between two compelling possibilities. Researchers like Tracy Slatire, a theoretical physicist at MIT who has extensively modeled the dark matter interpretation, embody the cautious excitement of the field. She has noted that while the signal is certainly consistent with a dark matter origin, the pulsar explanation is perfectly plausible as well. The scientific process has been a masterclass in meticulous analysis. Teams have searched for statistical evidence of point sources within the glow, a clumpiness that would betray the presence of individual pulsars. Some studies have claimed to find such evidence, arguing the excess is too lumpy to be smooth dark matter annihilation. Others have countered, showing that the alleged clumpiness is consistent with statistical noise and that the signal remains stubbornly smooth. The implications are enormous. If it's dark matter, it would be a revolutionary window into particle physics beyond the standard model, finally revealing the identity of 85% of the matter in the universe. If it's pulsars, it would be a stunning revelation about the star formation history of our galaxy's core, showing us that it was once a far more violent and productive place than we knew, littered with the corpses of dead stars. This ongoing saga, this meticulous passing of light from the abyss, is a perfect example of how science operates at the frontier. It is a slow, careful, and sometimes frustrating process of elimination, where the most exciting answer is held to the highest standard of proof. The galactic center excess is a ghost in the data, a whisper of possibility that has refused to disappear. It invites us all to follow along, to watch as new data from telescopes and new analytical techniques are brought to bear on the problem. It is a cosmic whodunit where the culprit is either a universe-altering new form of matter or a previously invisible population of stellar zombies. This dance between the extraordinary and the mundane, between new physics and hidden astrophysics, is a thread that connects this galactic mystery to other, even more energetic puzzles that lie beyond our own galaxy, in the deepest and most violent reaches of intergalactic space. Yet if the galactic center presents us with a mystery of unexpected light, the cosmic stage also holds the opposite extreme, regions of profound and unsettling darkness, voids so immense they feel less like empty space and more like a fundamental absence of reality itself. We have already ventured into the staggering emptiness of the Bootes void, but it is not alone in its isolation. Drifting through the constellation of Eridanus, the river, lies another colossal cosmic desert known as the Eridanus supervoid, a region of space so vastly underdense that it contains only a ghostly fraction of the galaxies a volume of its size should hold. While not as record-breakingly large as its cousin in Bootes, the Eridanus void is a critical piece of the puzzle, a second data point that confirms these staggering emptinesses are not freak accidents but integral features of the universe's large-scale structure. Its existence deepens the mystery, forcing us to ask not just how one such void could form, but why they seem to be a recurring architectural element in the cosmic web. To truly appreciate the character of this void, we must move beyond mere size and consider its texture and influence. Unlike the near-perfect spherical emptiness once imagined, modern mapping reveals these supervoids as complex, irregular shapes, more like amoebas or sprawling caverns than simple bubbles. They are not completely empty. They contain a sparse population of isolated, lonely galaxies, often strung along faint, tenuous filaments that stretch across the darkness like fragile bridges across an abyss. These galaxies are the true hermits of the cosmos, evolving in profound isolation, cut off from the gravitational tides and galactic collisions that typically drive star formation and evolution in denser clusters. Studying these isolated island universes offers a unique laboratory, a way to understand how a galaxy develops when left entirely to its own devices, free from the influence of its neighbors. The void itself, however, is more than just a backdrop. It is an active participant in the drama of light. As the ancient photons of the cosmic microwave background pass through these regions of underdense space, they undergo a subtle transformation. They must climb out of a gravitational well that is becoming shallower due to the influence of dark energy, a process that saps a tiny amount of their energy through the integrated Sachs-Wolf effect, leaving a faint, cold imprint on the CMB map. The Eridanus supervoid is actually a leading candidate for causing a portion of the famous CMB cold spot, directly linking these vast emptinesses to the most ancient light we can observe. This connection is where the Eridanus void, and others like it, transform from cosmic curiosities into essential tools for cosmologists. They are natural experiments for studying the most mysterious force in the universe, dark energy. The standard model of cosmology tells us that dark energy is the repulsive force causing the expansion of the universe to accelerate. But how exactly does it work? By meticulously measuring the shapes, sizes, and distributions of these voids, and precisely how they grow and evolve over billions of years, scientists can test the properties of dark energy itself. Does it have a constant strength, or does it vary over time? The rate at which these voids expand and stretch, pulled apart by the background expansion of the universe, holds the answer. Furthermore, the very presence of voids of such staggering scale helps refine our models of structure formation. They are the negative image of the dense galaxy clusters, the direct result of gravity pulling matter into filaments and nodes and leaving behind these corresponding deserts. Their size and number put stringent constraints on the initial conditions of the universe, the tiny quantum fluctuations from the Big Bang that were stretched to cosmic proportions during inflation. There is a profound, almost philosophical loneliness inherent in contemplating these places. To be within a supervoid would be to experience a universe utterly different from our own. The night sky would be almost black, with the nearest major galaxy a faint, blurry smudge of light millions of light years away. The dense tapestry of stars and nebulae that fills our own view from the Milky Way would be absent, replaced by a terrifying, pristine darkness where the true emptiness of the universe becomes palpable. This balance between the dense nodes of the cosmic web and these vast, empty regions is a fundamental characteristic of our reality. The universe is not a uniform soup. It is a fractal-like structure of clusters, filaments, and voids, each playing a role in the grand narrative of cosmic evolution. The voids are not mistakes, they are the necessary counterweight to the brilliance of the galaxies, the silent, expanding oceans between the islands of light. Their existence reminds us that creation and emptiness are two sides of the same coin, and that to fully understand the glittering structures of the cosmos, we must also learn to read the profound silence of the gaps between them. This exploration of cosmic emptiness, of the great nothing, now compels us to turn our gaze back toward the light, to the most violently energetic and transient phenomena in the intergalactic medium, where the silence is shattered by eruptions of power so immense they briefly outshine entire galaxies. From the profound emptiness of cosmic voids and the violent glow of the galactic center, we now turn to a structure of breathtaking elegance and symmetry that seems to defy the chaos from which it was born. Drifting through the turbulent heart of our galaxy, just 300 light-years from the supermassive black hole Sagittarius A*, is a cosmic sculpture of unimaginable beauty and precision, the Double Helix Nebula. In a region of space characterized by immense gravitational tides and explosive energies, this formation stands apart not for its raw power but for its stunning and familiar form. It is a vast, twisting ladder of dust and gas stretching across 80 light-years of space, and it bears an uncanny, almost impossible resemblance to the structure of a DNA molecule, the very blueprint of life itself. Its discovery in 2006 was a testament to the unique vision of the Spitzer Space Telescope. While other telescopes see the universe in visible light or other wavelengths, Spitzer was designed to see the infrared universe, the heat radiation emitted by warm dust and gas. This allowed it to peer through the obscuring curtains of dust that block our view of the galactic center in visible light. When astronomers, led by Mark Morris of UCLA, analyzed Spitzer's data, they found something that made them do a double take. There, amidst the chaos, was a clearly defined, double-stranded structure, coiled into a helix and perfectly aligned with the galactic disk. It wasn't a solid object, but a vast, intricate pattern woven from interstellar material, a cosmic fingerprint left by the invisible hand of magnetism. This is where the true mystery of the nebula lies. Its stunning shape is not the product of gravity or explosion, but of powerful magnetic fields. The prevailing theory suggests that the nebula is a visual manifestation of an enormous magnetic torsional wave, a kind of twist propagating through the fabric of space itself. At the heart of this theory is the fact that the gas and dust clouds at the galactic center are not floating freely. They are ionized, meaning they are electrically charged. This charged material becomes ensnared by the galaxy's powerful magnetic field lines. As the central bar of the Milky Way rotates, it drags these field lines along with it, but the immense gravitational influence of the central black hole resists this motion. The result is a colossal twisting effect, like wringing out a gigantic cosmic towel. This torsional stress creates a wave that travels outward, and as it moves, it organizes the illuminated dust and gas into that iconic double helical pattern we observe. It is a slow, majestic dance between rotation and gravity, with magnetism serving as the choreographer, creating order on a scale of light years. Yet, for all the elegance of this theory, the Double Helix Nebula remains a subject of active debate and fascination. The sheer perfection of its symmetry is what continues to baffle scientists. Cosmic processes are typically messy, producing irregular clouds and lopsided structures. To find something with such precise, mathematical regularity is exceptionally rare. Some researchers have proposed alternative mechanisms, such as the influence of a powerful jet from the central black hole interacting with surrounding clouds, or the shock waves from ancient, clustered supernova. However, none of these explanations account for the beautifully ordered, helical twist as effectively as the magnetic torsional wave model. The nebula stands as a brilliant and persistent riddle, a challenge to our understanding of how fundamental forces can conspire to create art on an interstellar canvas. Gazing upon its image, it is impossible not to feel a deep sense of awe that transcends mere astronomy. The resemblance to a DNA strand is so striking that it sparks a profound philosophical curiosity. Is this nothing more than a magnificent coincidence? A simple case of parallel patterns emerging from entirely different physical processes? Or does it hint at a deeper, more fundamental grammar of the universe, a universal tendency for certain forms, certain patterns of winding and weaving, to emerge across vastly different scales of existence, from the microscopic to the galactic? It invites us to consider whether the spiral, the helix, is a fundamental shape written into the laws of physics, a preferred solution that nature returns to again and again when organizing chaotic energy into stable, enduring forms. This cosmic artwork, born from magnetic fury near a black hole, reminds us that the universe is not only a place of violence and emptiness, but also one of breathtaking beauty and inexplicable order, where natural processes can produce structures that resonate with the deepest patterns of life itself. This contemplation of a perfectly ordered nebula now compels us to shift our gaze to formations born from pure chaos, where the forces of creation and destruction collide in a far more violent and unpredictable ballet. But if the Double Helix Nebula shows us how magnetic forces can sculpt order from chaos near a supermassive black hole, then our next destination reveals a different kind of cosmic artistry, one born not from the fury of a galactic core, but from the serene and intimate dance of two dying stars. Drifting 2,300 light-years away in the constellation Monoceros, the Unicorn, is a celestial object so geometrically perfect and chemically bizarre it has captivated astronomers for decades. This is the Red Rectangle Nebula, and its name, while descriptive, fails to capture the true profundity of this cosmic masterpiece. Through a telescope, it doesn't appear as a simple rectangle, but as a breathtakingly symmetrical structure of concentric rungs and sharp, angular corners, looking less like a cloud of gas and more like a vast, glowing ladder or an abstract stained glass window suspended in the void. This is not the chaotic aftermath of a random explosion. It is a structure of stunning precision, and its existence challenges our understanding of how stars die and what they leave behind. The heart of this mystery is a binary star system known as HD 44179. These are not young, vibrant stars, but two elderly suns in the final act of their stellar lives. One of them has exhausted the hydrogen fuel in its core and has swollen into a dying red giant, shedding its outer layers into space in a slow, relentless stellar wind. The presence of its companion star is the crucial ingredient that transforms this death throe into a work of art, As the two stars orbit one another, the gravitational pull and the outflowing material from the giant star are funneled and sculpted by the companion's influence. Instead of expanding outward in a simple, spherical shell, the gas and dust are forced into two opposing cones or lobes, creating a classic bipolar nebula. But the red rectangle is far from classic. What makes it unique is the astonishing regularity of these outflows. Astronomers believe that a dense, donut-shaped ring of dust, a torus, tightly encircles the binary pair at the center. This torus acts like a nozzle, constricting the expelled material and forcing it to shoot out perpendicular to the ring with incredible uniformity. The result is not a messy spray, but a series of seemingly perfect, concentric square-like structures that give the nebula its iconic name. Yet the nebula's mesmerizing shape is only half the story. Its intense, blood-red coloration is the other. This profound hue is not just for show, it is a direct signature of its bizarre and rich chemical composition. Spectroscopic analysis has revealed that the red rectangle is absolutely teeming with complex organic molecules known as polycyclic aromatic hydrocarbons, or PAH. These are not simple gases. They are sprawling, carbon-based molecules built from multiple interconnected rings of carbon atoms, essentially the basic building blocks of soot. But their presence here is a monumental clue. PAHs are considered fundamental precursors to the even more complex chemistry that can lead to the formation of life. Finding them in such abundance in a stellar nebula suggests that the death of sun-like stars is a prolific factory for the very ingredients necessary for biology. It forces us to consider a profound cosmic connection, that the end of one star system might literally be sowing the seeds for the beginnings of another, sprinkling the interstellar medium with the raw materials for future planets and potentially future life. This combination of perfect geometry and probiotic chemistry makes the red rectangle a unique laboratory for astrophysicists. Astronomers like Vincent Ike, who first theorized the hydrodynamic model that could create such square structures, have seen their ideas challenged and refined by its existence. The prevailing model suggests that the steady, rhythmic pulsations of the dying red giant, combined with the precise orbital dance of its companion, create periodic shock waves that travel through the outflowing gas. These shocks could compress the material at regular intervals, creating the ladder-like rungs we observe. However, maintaining such flawless symmetry over such vast distances and timescales is a hydrodynamic puzzle of the highest order. The system is a delicate balance of forces: gravity, radiation pressure, and stellar winds all working in concert to create an ephemeral sculpture that will eventually dissipate and enrich the surrounding cosmos. Contemplating the Red Rectangle Nebula invites a deeper reflection on pattern formation throughout the universe. How is it that turbulent, chaotic processes so often give rise to such ordered forms? From the double helix of a DNA molecule to the hexagonal storms on Jupiter, from the spiral arms of galaxies to the perfect concentric squares of this nebula, nature seems to have a preferred set of blueprints. The red rectangle stands as a powerful testament to this universal tendency. It shows that even in death, there can be extraordinary beauty and intricate order, and that the fundamental laws of physics, when applied under the right conditions, can produce art on a scale that spans trillions of miles. It is a dying star's final, magnificent statement, a message written in complex chemistry and perfect geometry, telling us that the universe has a hidden order and that even its endings are filled with the promise of new beginnings. But if the elegant structures of dying stars like the Red Rectangle Nebula represent a slow, predictable cosmic ballet, then the phenomena we turn to now are the universe's sudden, violent screams, brief eruptions of energy so immense they defy comprehension, and whose origins have become one of the most tantalizing puzzles in modern astronomy. These are fast radio bursts, or FRB. Imagine for a moment a source of energy so powerful that in the span of a single millisecond, a duration shorter than the blink of an eye, it can release more energy than our Sun does over 80 years. Now imagine that this staggering flash of radio waves has traveled across billions of light years of intergalactic space, only to be captured by our telescopes as a fleeting, brilliant spike on a graph. For years, these events were the ultimate cosmic ghosts, incredibly bright, utterly mysterious, and frustratingly one-off. The prevailing theory was that they must be the signature of a catastrophic, self-destructing event, a neutron star collapsing into a black hole, or two incredibly dense objects like neutron stars merging in a final, fatal embrace. These were the cosmic equivalent of a tree falling in an empty forest, a singular, final act that could never be witnessed again. This all changed with a single, game-changing discovery that shattered the cataclysm model and sent astrophysicists back to their drawing boards. In 2016, a team led by Laura Spittler using the Arecibo Observatory in Puerto Rico announced they had found something previously thought impossible, a fast radio burst that repeated. Designated FRB 1211-2, this source didn't just flash once and vanish. It erupted again and again with an unpredictable and seemingly random cadence. Sometimes it would remain silent for weeks, only to then fire off a dozen bursts in a single day. This single observation was a watershed moment. You cannot have a repeating cataclysm. A neutron star collision happens once. The existence of a repeater meant that whatever engine was powering these bursts was not only surviving the event, but was capable of producing these unimaginable energies multiple times. It was the crucial clue that transformed FRBs from isolated curiosities into a window onto some of the most extreme and dynamic environments in the universe. The immediate, frantic question was, where was this thing? Pinpointing the location of an FRB is a monumental challenge, as their fleeting nature makes them incredibly difficult to triangulate. But for FRB 1211-2, an international team using a global network of telescopes, including the massive Very Large Array in New Mexico, achieved a monumental breakthrough. They managed to precisely localize the repeating bursts to a tiny, dwarf galaxy over 3 billion light-years away. This was another stunning revelation. This wasn't happening in a large, mature galaxy like our own, but in a small, humble galaxy that was actively forming new stars at a prodigious rate. This environmental clue was like finding a specific type of rare fungus only growing on a certain kind of tree. It immediately pointed to the conditions necessary for the mysterious engine to exist. So what could possibly be behind these repeating, colossal shouts from a tiny galaxy? The prime suspect in the lineup is a type of neutron star known as a magnetar. Imagine the core of a massive star collapsed into a sphere the size of a city, but with a density so immense that a single sugar cube-sized piece of it would weigh more than 1 billion tons. Now take that object and imbue it with a magnetic field 1,000 trillion times more powerful than Earth's. This is a magnetar, a cosmic powerhouse where the magnetic energy is so intense it can literally twist the star's crust, causing starquakes that rip open its surface and release titanic flares of radiation. A particularly violent magnetar flare could easily account for the energy of an FRB. The repeating nature could be explained by the magnetar undergoing periodic upheavals, its crust cracking again and again under the strain of its own unimaginable magnetic field. This is a compelling and elegant natural explanation, and the discovery of an FRB emanating from a known magnetar within our own Milky Way galaxy in 2020 provided strong supporting evidence for this model. Yet, the mystery is far from completely solved. The sheer diversity of FRB signals, some repeating, some not, some showing incredibly complex patterns within their millisecond structure, others appearing much simpler, suggests that we might not be dealing with a single source, but perhaps a family of related phenomena. Could some FRBs be from magnetars while others are from different, even more exotic engines? Some theorists have proposed colliding neutron stars in tight binary systems, or asteroids being torn apart as they fall onto a neutron star. And then, of course, the sheer power and brevity of the signals inevitably lead to more speculative, yet utterly captivating possibilities. As pioneering FRB researcher Duncan Lorimer has noted, while the natural explanations are far more likely, the properties of these bursts are consistent with what we might expect from an artificial beacon, a powerful interstellar lighthouse, or a byproduct of inconceivably advanced technology. This isn't a scientific conclusion, but it is a powerful reminder of how these discoveries push our imagination to its limits, forcing us to confront the possibility that the universe is far stranger than we ever dreamed. The detective work continues at a feverish pace. Every new repeating FRB that is discovered adds another piece to the puzzle, helping astronomers understand the range of environments and behaviors these objects exhibit. They are not just cosmic oddities, they are powerful tools, as these radio waves traverse the vast, empty spaces between galaxies. They are subtly dispersed and delayed by the tenuous sea of electrons they encounter. By measuring this dispersion, scientists can actually use FRBs as probes to weigh the invisible matter in the cosmos, providing an independent check on our measurements of the universe's missing baryonic matter. The repeaters, with their known and fixed locations, are especially valuable for this cosmic cartography. Each burst is a flashbulb illuminating the dark corners of the universe, revealing the fabric of intergalactic space itself. This incredible utility, born from such a profound mystery, now sets the stage for an even more elusive class of signal, the one-off bursts that started it all, whose singular nature may point to an origin even more violent and final than we first imagined. But if the repeating fast radio bursts offer a tantalizing window into the lives of extreme objects like magnetars, then their far more common and enigmatic cousins present a mystery of an entirely different nature, the one-off, non-repeating burst. These are the cosmic flashes in the pan, the singular, millisecond-long screams of radio energy that erupt from the depths of space and then vanish forever. They offer no second chance, no opportunity for follow-up observation. They are the ultimate celestial ephemera, and their fleeting, self-destructing nature points to origins that are not just powerful, but profoundly final. The defining characteristic of these non-repeating FRBs is their sheer, uncompromising singularity. A telescope might detect a burst of immense power, a spike of energy that screams across billions of light years, and then nothing. Astronomers can point every instrument they have at that same patch of sky for years afterward, and be met with only an unnerving silence. This one and done behavior is the crucial clue that separates them from the repeaters. It strongly suggests that whatever event caused the burst was so cataclysmic, so utterly destructive, that the source itself was obliterated in the process. It is the difference between a volcano that erupts periodically and a bomb that detonates just once. This has led astrophysicists to a suite of theories that read like a list of the most violent finales in the cosmic playbook. The leading candidates include the spectacular merger of two ultra-dense objects, like neutron stars or a neutron star and a black hole, events so energetic they warp the fabric of spacetime itself and send out gravitational waves. Another possibility is the catastrophic collapse of a supermassive neutron star into a black hole, a final, desperate act where the star's immense magnetic fields are snapped and released in a last, brilliant flash of radio light. These are events that cannot happen twice because the objects involved cease to exist. Studying these solitary flashes is one of the most formidable challenges in modern astronomy. Their brevity is their greatest defense against understanding. A millisecond is an eye blink in human terms, but for a telescope trying to pinpoint a location across the universe, it is an agonizingly short window. The race is to capture the burst signal across multiple dishes simultaneously, a technique called interferometry, which allows scientists to triangulate its origin to a specific galaxy. This is where instruments like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have revolutionized the field. Unlike traditional telescopes that stare at a small patch of sky, CHIME is a stationary, cylindrical array that acts like a cosmic fish-eye lens, scanning the entire northern sky every day. Its design is perfectly suited to catching these fleeting events, and it has already catalogued thousands of FRBs, the vast majority of which are of the non-repeating variety. This immense dataset is the first step toward building a statistical understanding of these phenomena, moving from curious anomalies to a quantifiable class of cosmic events. Yet the true value of these mysterious bursts may lie not in their source, but in their journey. Every single FRB, before it reaches our telescopes, has traversed an almost unimaginable gulf of intergalactic space. This space is not a perfect vacuum. It is filled with an incredibly diffuse soup of ionized gas and electrons. As the radio waves travel, they interact with this material, causing different frequencies to arrive at slightly different times. This effect, called dispersion, creates a characteristic smear in the signal. By meticulously measuring this smear, astronomers can actually use the FRB as a probe. The amount of dispersion directly tells them the total number of electrons the signal passed through on its way to Earth. It's like being able to weigh the fog by how much it dims a distant lighthouse. This turns each non-repeating FRB, however brief, into a powerful tool for cosmic cartography, allowing scientists to map the distribution of the elusive missing baryonic matter believed to be hiding in the warm, hot intergalactic medium. The growing catalogue of these events reveals another layer of intrigue: their staggering diversity. No two non-repeating bursts look exactly alike. Some show incredibly complex internal structure within their millisecond duration, with multiple sub-peaks and dips, suggesting a highly structured and violent origin. Others are much simpler, clean spikes of energy. This wide variation strongly hints that we may not be looking at a single type of event, but a whole spectrum of cataclysms. Perhaps the merger of two neutron stars produces a burst with one signature, while the collapse of a magnetar produces another with a different energy profile and dispersion measure. The non-repeating class might be a catch-all category for the universe's most dramatic and final explosions, a cosmic graveyard filled with the last shouts of 100 different kinds of stellar deaths. This incredible diversity of cosmic transients, from the repeating, periodic shouts of magnetars to the singular, final screams of merging stars, teaches us a profound lesson about the universe. It is a place of constant dynamic change, filled with events operating on timescales from billions of years to mere milliseconds. Each flash, whether it repeats or not, is a message. Some messages are like an ongoing conversation, allowing us to slowly decipher their meaning. Others are like a single, emphatic word shouted across a canyon, leaving us to forever wonder about the context. But in their brief brilliance, they all illuminate the dark, revealing the structure of the vast nothingness between galaxies and hinting at the violent, beautiful processes that shape cosmic evolution. And as we learn to listen to these millisecond messages, we are inevitably drawn to other, more persistent signals from the void, enigmatic whispers that last not for a moment, but for decades, patiently waiting for us to understand their source. Yet while the violent, millisecond drama of fast radio bursts captures headlines, a far more subtle and persistent mystery has been humming in the infrared spectrum for decades, a set of spectral signatures so widespread and enigmatic that they represent one of the most fundamental puzzles in astrochemistry. These are the unidentified infrared bands, or UIB, a series of faint emission lines that paint a ghostly fingerprint across the galaxy, detected in the vast clouds between stars, in the swirling disks around young suns, and even in the atmospheres of other galaxies. Unlike the singular blast of an FRB, the UIBs are a constant cosmic chorus, a whisper of complex chemistry happening on a galactic scale. Their story begins not with a dramatic discovery, but with a slow, dawning realization as infrared astronomy matured in the late 20th century. Every time astronomers pointed their sensitive infrared detectors at a region of space rich in gas and dust, these same spectral bands would appear, a set of peaks at very specific wavelengths like a musical chord played on a cosmic organ. The signal was clear, persistent, and utterly baffling. The central clue to this mystery lies in the precise wavelengths of these emissions. They correspond to the vibrational energies of specific molecular bonds, the stretching and bending of atoms held together. The pattern pointed unequivocally to organic chemistry, to molecules built around rings and chains of carbon atoms. The leading and most compelling hypothesis is that we are seeing the collective glow of polycyclic aromatic hydrocarbons, or PAH. Imagine these not as simple molecules, but as tiny, flat flakes, like microscopic pieces of graphene or soot, each one a miniature hexagon-filled network of carbon atoms fringed with hydrogen. When a single photon of starlight strikes one of these flakes, it vibrates with the energy and re-emits it at these very specific infrared signatures. It's as if the universe is filled with countless infinitesimal tuning forks, all ringing in harmony whenever starlight strikes them. This explanation is elegant, but it is far from complete. The term unidentified infrared bands persists for a very good reason. While PAHs are the prime suspects, no single, specific pH molecule has been definitively matched to the entire observed set of bands. We are hearing the chorus, but we have not yet identified every individual singer in the choir. This uncertainty opens a door to a much deeper and more fascinating debate. If they are PAHs, how did they form in such abundance? Are they forged in the violent, hot outflows of dying stars like the Red Rectangle Nebula, cooked in stellar furnaces, and then blasted into the interstellar medium to spread their chemical seeds? Or could they form through slower, more complex chemistry right on the surface of cold dust grains in the darkest, most frigid molecular clouds? The distribution of these bands adds another layer of intrigue. They are not everywhere equally. Their strength and subtle shape change depending on their environment, whether they are bathed in the harsh, ultraviolet light near a massive star or sitting in the relative quiet of a dark cloud. This variability is a goldmine for astrochemists. By studying these changes, they can effectively take the temperature of the interstellar medium and understand the intensity of the radiation fields that shape the evolution of galaxies. It's a powerful diagnostic tool, turning a mystery into a measuring device. The profound implication of the UIBs, regardless of their exact identity, is that the universe is seemingly awash in the raw materials for life. The sheer ubiquity of these large, complex organic molecules suggests that the basic carbon-based chemistry that led to life on Earth is not a rare, local anomaly but a universal process. These molecules are the inevitable, widespread fallout of stellar evolution and galactic ecology. Astrochemists like Els Peters and Alexander Tylens have spent careers mapping these signatures, seeing them as traces of a grand cosmic carbon cycle. They represent a crucial step up the ladder of chemical complexity, from simple atoms like carbon and hydrogen to large, stable structures that can act as platforms for even more intricate reactions. They are the cosmic soot that could one day become part of a planet, an ocean, or even a living cell. Contemplating this changes our perspective on the darkness between the stars. It is not a true void, it is a vast, diffuse chemical reactor simmering with organic potential. The UIBs are the detectable signature of that simmering, a constant reminder that the universe is not only physically structured by gravity, but also chemically primed for complexity. This revelation that the building blocks of life are a common, almost mundane feature of the galaxy forces us to look even deeper, to ask what happens when these simple organic molecules are given the chance to combine and grow into even larger, more complex structures in the perfect cosmic laboratories, dense molecular clouds, and protoplanetary disks. Tucked away in the cosmic currents near the spiral galaxy NGC 2683, drifting through the constellation links, lies a ghost. It is not a remnant of a dead star, but an entire galaxy that seems to be doing its utmost to avoid detection. This is the Goblin Galaxy, officially catalogued as UGCA 193, a name that perfectly suits its elusive, almost spectral nature in the night sky. Unlike the majestic spirals or the glowing ellipticals that dominate our telescopes, the Goblin is an irregular galaxy, a faint, shapeless smudge of light that challenges not only our ability to see it, but our very understanding of what a galaxy can be. Its discovery story is a testament to how much of the cosmos still hides in plain sight, waiting for our technology and our persistence to catch up. It wasn't found in a grand, targeted search, but was instead picked up in the faint background of surveys aimed at brighter, more obvious neighbors, a cosmic afterthought that has since become a focal point of intense study. What makes the Goblin so fascinating to astronomers isn't its brilliance, but its profound dimness. It belongs to an enigmatic class of objects known as ultra-diffuse galaxies, or UDG. The name is a precise, if dry, description. These galaxies have an extremely low surface brightness, spreading their stars so thinly across a vast volume of space that they blend almost perfectly into the blackness of the intergalactic background. The Goblin, for instance, is about the same overall width as our own Milky Way, but it contains perhaps only 1% of the stars. Imagine our galaxy, with its hundreds of billions of suns, being stretched out into a wispy, ethereal cloud where the average distance between stars is millions of times greater. This incredible sparseness is the heart of the mystery. According to our standard models of galaxy formation, a structure this large should have collapsed under its own gravity long ago to form a much denser, more compact object, or it should have been ripped apart by the gravitational tides of its larger neighbors. The fact that it exists at all, and that we are finding more and more galaxies like it, forces a major revision of our cosmic playbook. The central puzzle revolves around dark matter, the invisible glue that holds all galaxies together. The prevailing theory suggests that all galaxies, from the largest spirals to the smallest dwarfs, are embedded within vast, massive halos of this mysterious substance. Its gravity provides the scaffolding that allows normal matter to coalesce and form stars. For a galaxy as large and diffuse as the Goblin to exist, it must be embedded in an incredibly massive dark matter halo to hold its sparse stars in such a wide orbit. Yet, observations of its dynamics show a perplexing discrepancy. The motions of its stars don't always indicate the amount of dark matter we would expect to find. This leads to a fierce debate among astronomers. Is the Goblin Galaxy a failed galaxy, one that somehow formed with a huge dark matter halo but was incredibly inefficient at turning its gas into stars? Or is it a dark matter-free galaxy, a notion that would be even more revolutionary? This second theory proposes that the Goblin could be a tidal dwarf, a galaxy not born from its own dark matter seed, but ripped and pulled from the material of a larger galaxy during a violent collision, leaving it composed almost entirely of normal matter and vulnerable to the gravitational forces around it. This ambiguity is what makes the study of ultra-diffuse galaxies like the Goblin so critically important. They are natural laboratories for testing the extremes of galaxy formation and the fundamental properties of dark matter. Every new one we find adds a data point, helping us understand whether they are all the same or if they represent a diverse family with multiple origins. The Goblin itself, with its unusual and patchy star formation patterns, suggests a turbulent history. Some pockets within it are actively birthing new stars, while vast regions lie fallow and quiet, hinting at a past shaped by external forces, perhaps an ancient, gentle encounter with another galaxy that stirred its gas without completely tearing it apart. The public nickname, the Goblin, itself plays a role in this scientific narrative. While its official designation is a sterile string of letters and numbers, a memorable moniker captures the imagination, reminding everyone that these are not just abstract data points but real, mysterious places in the cosmos, worthy of curiosity and wonder. It embodies the thrill of the hunt, the idea that our universe is still filled with hidden monsters lurking just beyond the edge of our vision. And this is perhaps the most exciting implication of the Goblin Galaxy and its ilk. If such a large, nearby object remained hidden for so long, how many more are out there, drifting unseen in the voids between the brighter galaxies? Each new deep sky survey, each more powerful telescope, seems to uncover more of these cosmic phantoms, suggesting they might be one of the most common types of galaxy in the universe. Their sheer numbers would force us to completely reassess the population census of the cosmos and acknowledge that the universe has a strong preference for subtlety over spectacle. They represent the quiet, majority population of the galactic realm, a shadow universe of faint giants that has been there all along, waiting for us to develop the eyes to see them. The Goblin Galaxy is a humble, faint whisper from the darkness, but its message is deafening. Our understanding of cosmic structure is incomplete, and the most common building blocks of the universe may be the ones we have been overlooking. This exploration of the faint and diffuse now compels us to turn our gaze to the opposite extreme, to the most massive and violent collisions in the universe, where galaxies don't hide but instead scream their existence in a spectacular, fiery demise. Yet Hoag's object is not the universe's only celestial eye gazing back at us from the void. Across the cosmos, other ring galaxies and pseudo-ring structures present variations on this mesmerizing theme, each with its own story of cosmic violence or serene evolution that helps us piece together the complex puzzle of galactic life. Take AM 06444741, for instance, often nicknamed the Lindsay-Shapley Ring after its discoverers. Located 300 million light-years away, this galaxy presents a spectacle of breathtaking contrast to Hoag's serene perfection. Where Hoag's object is a symmetrical, isolated wonder, AM 06444741 is a product of utter chaos, a clear and stunning example of a bullseye galaxy formed by a direct head-on collision. In this violent ballet, a smaller intruder galaxy has punched straight through the heart of a larger disk galaxy. Like a rock thrown into a pond, this collision sent a powerful density wave rippling outward through the target galaxy's disk. This wave compresses the gas and dust it encounters, triggering a firestorm of new star formation that lights up in a brilliant blue ring of massive young stars, while the older, yellower stars of the original galactic core remain relatively undisturbed at the center. The perpetrator galaxy, having delivered its devastating blow, can often be seen fleeing the scene of the crime, a faint smudge of light outside the magnificent ring it helped create. The existence of these two distinct ring types, the pristine, isolated Hoag type and the collision-born cartwheel type, forces astronomers to grapple with a spectrum of formation mechanisms. For the violent rings, sophisticated computer simulations have become an indispensable tool, allowing scientists to reenact these cosmic crashes billions of times, tweaking the angle, speed, and mass of the colliding galaxies until the simulation perfectly matches the telescope's image. These digital recreations reveal that the perfect circular ring of Hoag's object is an extreme rarity, requiring a near-perfect perpendicular impact. More often, collisions are glancing blows, resulting in warped, asymmetric rings, or even structures with multiple rings or broken arcs, each one a frozen moment in a billion-year-long demolition derby. This is where the concept of resonance comes into play, a subtle gravitational dance that can shape a galaxy without a direct hit. Just as Saturn's gravity creates gaps in its rings and Jupiter's gravity shepherds asteroids in orbital resonances, a close gravitational encounter between two galaxies can set up persistent density waves within a galactic disk. These waves can organize the gas and stars into ring-like structures through a process called secular evolution, a slow, internal transformation driven by the galaxy's own asymmetries and gravitational instabilities, such as a central bar. This gentler process might be the key to explaining the few perfect, undisturbed rings like Hoag's object, suggesting that not all cosmic beauty requires a violent birth. Beyond the visible spectacle of stars, these ring galaxies serve as crucial probes for the invisible architecture that holds them together, dark matter. The stability and longevity of a ring structure, whether created by collision or resonance, depend entirely on the gravitational framework of the galaxy's dark matter halo. This unseen scaffold provides the necessary gravity to keep the ring from simply flying apart or dissipating after the initial wave has passed. By studying the rotation speeds of stars and gas within these rings, astronomers can map the distribution of this dark matter. The results often reveal halos that are not simple spheres but are flattened or elongated, their shapes influenced by the same ancient interactions that forged the visible ring. In this way, the brilliant rings of stars act as luminous tracers, outlining the gravitational influence of the invisible, allowing us to study the dark side of the universe through the behavior of the light. Contemplating this menagerie of ringed galaxies, from the perfect solitude of Hoag's object to the chaotic artistry of collisional rings, invites a profound appreciation for the dynamic and ever-changing nature of the cosmos. It reveals a universe that is both a destructive force and an unparalleled artist, capable of forging breathtaking beauty from both violent catastrophe and slow, patient evolution. Each ring is a chapter in a grand narrative of gravitational influence, a story written in starlight and dark matter, reminding us that a galaxy's form is not a static portrait but a fleeting moment in a billion-year dance. This understanding of galactic diversity and transformation is the final, crucial piece that prepares us to step back and behold the entire cosmic tapestry we have been exploring, to see the profound connections between the universe's largest structures and its most intricate designs. So where does this leave us, confronted with a universe that seems to be filled with both impossible structures and inexplicable silences? When faced with a cosmic mystery, from a perfect ring of galaxies to a fleeting radio scream, science employs a spectrum of possibilities, a ladder of explanations that ascends from the comfortably familiar to the breathtakingly speculative. On the lowest, most grounded rung, we find the tried and tested forces of astrophysics, amplified to scales we are only beginning to comprehend. The Great Attractor is likely a supercluster, its pull a testament to the raw, collective gravity of thousands of galaxies. The Fermi Bubbles are almost certainly the remnants of a titanic eruption from our galaxy's central black hole, a belch of cosmic energy on a scale that defies earthly analogy. For many of these phenomena, the answer doesn't require new physics, merely a deeper appreciation for the staggering power and subtlety of the physics we already know. This is the guiding principle of Occam's razor, the idea that the simplest explanation, the one that requires the fewest new assumptions, is most often the correct one. It is the bedrock of scientific skepticism, a necessary filter against seeing patterns in every random noise. But what happens when the simplest explanations consistently fail to fit the data? When a structure is so large it violates cosmological principles, or a signal is so precise it feels engineered? This is where we must cautiously ascend to the next rung of the ladder, to the realm of the not yet known. This isn't a leap to aliens, but a step into the frontier of theoretical physics. The Hercules corona Borealis Great Wall might be explained by exotic inflationary models or primordial defects in space-time cosmic strings left over from the universe's birth. The dark flow could be evidence of a gravitational tug from a region of space beyond our observable horizon, perhaps even from another universe in a vast multiverse, a concept that, while staggering, is being seriously explored by cosmologists. These ideas are not wild fantasy, they are mathematical hypotheses, extensions of our current models that are being stress-tested against these very anomalies. They represent science at its best, boldly following the data, even when it leads to uncomfortable and paradigm-shifting conclusions. And then there is the highest rung, the most speculative but utterly captivating realm of possibility, technosignatures. This is not the science fiction trope of little green men in flying saucers, but a serious, if fringe, field of study grounded in scale and physics. The concept, popularized by thinkers like Freeman Dyson and Nikolai Kardashev, asks a simple question: what would the energy signature of a civilization that had mastered its planet, its star, or even its entire galaxy look like? Could the precise dimming of Tabby's star be the shadow of a partially constructed Dyson swarm, a civilization harnessing the power of its sun? Might the inexplicable timing and energy of a non-repeating fast radio burst be the catastrophic discharge of an interstellar propulsion system of unimaginable power? These are not claims, they are thought experiments, the ultimate application of Carl Sagan's famous admonition that extraordinary claims require extraordinary evidence. The evidence is not there yet, but Sagan also championed the balance between a skeptical mind and a sense of wonder, between rejecting easy answers and remaining open to the universe's infinite potential for surprise. To dismiss these possibilities out of hand is to ignore the profound lesson of Copernicus. We are not the center of the universe, and our current technological maturity is likely not its peak. This relentless pursuit of answers, wherever they may lead, is the engine of human progress. Each one of these mysteries directly fuels technological innovation. The search for the missing Baryons drove the design of the Chandra and XMM Newton X-ray observatories. The hunt for the nature of dark energy was the primary scientific motivation for the Nancy Grace Roman Space Telescope. The need to localize fast radio bursts is pushing the development of immense, multi-dish radio arrays like the Square Kilometre Array. And the overwhelming torrent of data from these new instruments is now being sifted by artificial intelligence, algorithms trained to find the subtle, non-random patterns that might escape the human eye, whether they be the gravitational lensing signature of a primordial black hole or the statistical whisper of an artificial broadcast. We are building ever bigger ears and ever sharper eyes, not because we know what we will find, but because we know we have not found everything. This brings us to a final, reflective question about our place in this grand investigation. Are we merely passive observers cataloging a universe that unfolds independently of our gaze, or is there a deeper, more participatory role we play? The act of observation, of asking a question of the cosmos, seems to compel it to reveal a new layer of complexity. For centuries, we saw stars as simple points of light. Only when we asked what they were did we unlock nuclear fusion and stellar evolution. We saw space as an empty void. Only when we asked how galaxies moved did we discover the dark matter that binds them. It is as if the universe holds its secrets in reserve, not out of spite, but waiting for a consciousness sophisticated enough to form the right question. The enigmas we explore today, the voids, the flows, the impossible structures, may not be mere puzzles to be solved. They may be the next set of questions posed by the universe itself, inviting us to look deeper, think broader, and evolve our understanding once more. The greatest discovery may not be a what but a why, revealing not just how the cosmos works, but if it has, in some ineffable way, been waiting for us to finally understand. From the silent, watchful presence of the Great Attractor pulling our entire galactic neighborhood toward an unseen destiny, to the staggering, impossible scale of the Hercules Corona Borealis Great Wall that seems to defy the universe's own rulebook, we have ventured across a cosmos far stranger than we ever imagined. We have stood in awe of perfect celestial forms like Hoag's object, witnessed the explosive history of our own galaxy written in the gamma-ray light of the Fermi Bubbles, and tried to decipher the fleeting, millisecond screams of fast radio bursts that could be the death cries of stars or something else entirely. Each of these structures, from the yawning emptiness of the Bootes void to the precise, mathematical dimming of Tabby's star, serves as a stark reminder of the boundaries of our current knowledge. They are not merely puzzles to be solved, they are profound challenges to our fundamental assumptions about physics, reality, and our place in the grand scheme of existence. What unifies these disparate enigmas is not a single answer, but a shared sense of awe at the universe's boundless complexity and a celebration of the human spirit that refuses to accept easy explanations. Whether the final answer for each mystery lies in the violent but natural drama of colliding neutron stars and erupting black holes, or in the more speculative realm of cosmic engineering and technosignatures, the value of the pursuit is immeasurable. These mysteries are the sharp edge of discovery, the points of friction where our models break down and new physics is born. They force us to build better telescopes, design more sensitive detectors, and train sophisticated artificial intelligence to sift through the noise of the cosmos for the faint signals of truth. This relentless curiosity is our greatest inheritance, a drive to look into the darkness and not only ask what is there, but to dare to go and find out. This journey underscores a beautiful and humbling paradox. The more we learn about the universe, the more we are confronted by how much we have yet to understand. The cosmic web, with its filaments of dark matter and glowing galaxies, is both a map of what we know and a diagram of the profound gaps in our knowledge. The search for the missing baryons teaches us that even the ordinary matter we're made of can hide in plain sight. while the axis of evil whispers that the universe might have a preferred direction after all. These are not failures of science, but its ultimate triumph, a demonstration that the universe is a dynamic, evolving conversation, and we are only just beginning to learn its language. Public engagement from the citizen scientists of Galaxy Zoo who found the green pea galaxies to the thousands who crowdfunded the observation of Tabby's star proves that this wonder is not confined to laboratories. It is a universal human trait, a shared desire to be part of this grand story of exploration. As we bring this exploration to a close, we are left with a sense not of finality, but of infinite potential. The cosmos is not a static picture to be analyzed, but a living, breathing mystery that invites us to keep questioning, keep searching, and keep wondering. It brings to mind the words of the visionary astrophysicist Neil deGrasse Tyson, who so perfectly captured this sentiment. The universe is under no obligation to make sense to you. And yet, here we are, striving to make sense of it anyway, driven by an insatiable curiosity that is, itself, a fundamental force of nature. This is the true legacy of these mysterious structures. They are not just features of space, but beacons that guide us toward a deeper, more profound relationship with the reality we inhabit. So we encourage you to carry this wonder with you. Share your own thoughts and questions in the comments below. Subscribe for more deep dives into the universe's greatest enigmas, and never stop looking up at the stars with that same sense of awe and endless curiosity. The next great cosmic secret is waiting, and it will reveal itself to those who are prepared to